Oh, hey, all good here? Hey, yeah. This is inconvenient. Probably move it somewhere.
Yeah, sure.
Yeah. There's so the AC guy, so they should switch it on.
Oh,
The
okay,
AC,
okay.
yeah.
Good. I thought we do.
Yeah, it shouldn't be like that, so it should be
I didn't know if it was like expected to be like this.
No, it's just like the building facilities they screw up because it should have started at 8.
Yeah, sure. Ja. 啊，多次，可以可以。
Are you one of the presenters?
I'm the chair, one of the chairs.
Are you just a resident?
Sorry?
Are you going to stay in this room?
I think so, because this is the Erlang room. So
Okay. Ian, by the way, nice to meet you. What's your name?
what's your name again?
Ian.
Ian.
Y-I-N-G.
What?
Are you Spanish?
Yes, yeah, I'm from
What's your name?
Kiko.
Kiko. Nice to meet you.
Are you a student or organization?
I'm students from the US. Are you you are not student? Are you
No.
professor of the US?
No, I work now at Ericsson. So I did my PhD in Sweden.
Oh, nice.
The national.
And now you are in the industry.
Yeah, I'm in industry.
Okay. What kind of product you are doing?
We work on the Erlang programming language.
Erlang.
Yeah, so this is language. And used by WhatsApp.
Erlang. Do you work with Amadeus?
No.
No. Because Amadeus is also a Spanish company with the global distribution for reservation for that.
Yeah, exactly. That's what I thought. No, but I don't know if they cover.
You don't work with them. How the language is used in Erlang in the trailer?
Sorry, how's it?
So you are working with Erlang in like which sector?
So Erlang is the programming language. It's like working with Python. We develop the programming language.
Oh, you develop a specific language for the
Communications. This was like 40 years ago.
for communication of the Erlang.
No, he's maintaining the Erlang language, right?
Erlang. Oh yeah, sorry. Erlang language.
It's super.
Yeah, it is.
No, I
but-
understand what you
It
said.
Yeah, no, I traveled with an infinite supply of shirts. Right?
Yeah,
because
I
that's.
should have known that.
You're also one of the maintainers.
No,
Come again?
he's not.
No. I'm just a speaker
So
here.
use of the language. Yeah.
Well,
Have
yeah, occasionally. I guess more of a fan of the language than I am a user of the language because I don't have a good use for it right now. Like we start at 9 sharp, right?
Yeah, that's what they said.
And I started 1:15.
Yeah.
Yeah, great.
So you are the first presenter, right?
Yes.
Do you want to be streamed and recorded?
I don't know. I mean, like I'm fine either way. What does the workshop want? Do you want to stream and record?
I think we are supposed to stream unless you decide not to stream to us.
Yes. By default.
No, I've signed all of the waivers and stuff, right?
Okay,
So
so then.
yeah. So stream.
Okay. Do you want to use your own device or?
I need to use my own device. Yes.
Maybe we should pass this.
But I have lectured in this very room before, so
Oh, that would be
I should
much
be,
easier.
I should be good.
But the AC is not working, right?
No, I think it's not on.
Yeah.
I think it's Sunday, right?
Yeah. Ilya came and said that they were supposed to switch it on for the whole building at 8.
Do you need the audio from?
Let's do. No, I'm not gonna use audio.
Okay, so maybe you should mute yourself when you join the Zoom.
Oh, sorry. I should join the Zoom. Got it.
Oh, no, if we already have it connected to yours, you should join the Zoom so you can share the screen.
That. Yes.
Meeting ID.
Right. Okay. So then let's join this.
I apologize, I didn't realize that he's the creator of Erlang.
Well, it's not the creator. I think the
It's
creator,
not?
the creator has died, but
No.
but his creation lives on through Kiko. Right?
Okay, the main maintainer of the Erlang.
Yeah, or I mean, one of them. It's like a team at Ericsson of I don't know how many are you? Kiko, like 15 people.
In the team, yeah,
Yeah.
15 to.
50 to maintain the languages.
Right now, class common, so that's 9, 5, 7, 4, 6, 1. Let's see. Just get that right. No, okay. One more time. 9, 5, 7, 4, 6. Yeah. Okay.
Nice picture though.
Yes. So then. All right, but I mute myself. I don't use video. It's only sharing the screen,
Yes,
right?
yes. So now you can share it.
Okay.
And we need to do the opening, so is it easy to switch between the Dropbox and then to your computer?
On the main computer.
Oh, do you have slides?
Yeah, but otherwise we do it without.
Why don't we put the slides on my machine? And
Yeah, that's what I think.
Great,
I can
that's
send you the link
Yeah.
Yeah.
because it's just a PDF. So I can send you.
you will you Slack it to me?
Right, I can flash this.
Yeah.
Oh, where is it now?
Any issue?
No, not as I see so far. So we are trying to present from his device.
Yeah.
And we just need to share the screen, right, from.
Yeah, exactly. So I go on Zoom, share my screen, and then let's go to. Right, so now that's all shared, that's fine. If I go to my software, so Sam.
Visual results, and all those things.
So when you go right. This it works, yeah, okay, so we all good?
Oh, okay. Yeah, it's one.
Oh, the camera and the mic is that one, I think.
It's all together.
Yes.
For you.
Good.
I think I'm getting it.
Okay, up to you.
Thank you.
For someone is anything wrong.
To be once a week. I knew it was talking about
You're also coming from
yeah, well, in Spain, it's completely the opposite. But this is just we. What good I want myself to not watching movies during the film that we follow. And then it's like to switch this. Not how to
It's
If I can do it.
I'm wondering whether it's Sunday. Sunday, let me see. I'm not sure if I can wait.
I don't know what one
We have a ton of workshops.
I just looked at it and.
It's the same as last year.
Pardon?
Sure.
No. And also, yeah. Ora.
I have just here 11. So then I stayed over to them again. I went to Sentosa. I was looking to get on the road. I didn't like it that much. I thought it was way too prestige. I was expecting more nature, but by the school. Or walk them. No, because we were thinking, we don't need that for you. We don't know what to do. I don't say. Yeah, but it's waiting for that to be. I used to be able to cope with them. So I can see other things. Now we're thinking, hopefully, okay. It's in winter because it's still February. But this. Exactly. Because if we go in June or something, again, it's 30 degrees. You know, I prefer the cold.
Yeah.
I don't care if it's snowing or something. Yeah. Yeah. Anything. That's yeah. Let me see if I find because I need to email this to yes, so that way he has the notification.
Oh, okay.
I need to look for. Oh, this is looking good, right? Pico. Yeah.
Yeah.
Okay, we will send you a new PDF because of the date. Should be.
So, or do you want to change this
Yeah.
date? Okay.
I think that's a minor change.
Guess we're also streaming the minor change, so that's fine.
Have you sent the?
No, no. Então,
The only change, Kiko, is the only change on the first page?
mostly, I think.
That's a no. Okay, cool, no problem.
And look at the public course, with interpretation, $90. Yeah, I don't know if it can be heard. And I think that's.
It was the right one, because I saw it, but it were rolling.
Yeah, that's how it's. Yeah.
That's it.
And that was off peak, so if you take anything from 6 p.m. over, then it was under 20%. Yeah, I know it's 40 dollars or so. Yeah. You know, we don't have this 60 euros, that's sort of 50%. Like that's. Yeah.
It's really good. It went right on yesterday.
I wanted to read you this morning. I probably don't have. I worked at 6 on the this week. With 2-3 minutes, I shot more for sure. Maybe I talked about Singapore and I said, no, he said, no, but he thought, why not? Well, you need to fight from Barcelona, so I don't know.
So you are one of the organizers, right?
Yes, yeah.
Because I also be presenting today.
Yeah.
I'm here.
Yeah.
Okay. So. So mine is at 11.
Probably.
Yeah. Yeah. Okay.
So yeah, I think that the most of Amazon's volume. So many people over here. But if I can go, I can, but I can just go. I think we won't be to like. You know, work about 3 million. That's okay.
It's gonna be tough. But I don't know how old it's gonna be. I feel like it's.
Right, yeah, like but yeah, I take a swing and I go, I don't know how to process.
Are you all from Harrison?
I'm from here.
Oh.
I don't know. Your reservations. I know that's so many people at home, so. You do French. I work with them.
Yeah, he's not coming because of that, but maybe he will go to.
I don't know if you always. No,
But it's time we can much better.
Yes.
was setting up a meeting for your configuration on maybe.
I don't know if it's.
Oh, maybe.
Some discussions about.
No, remember.
Yes, but I don't know if it was.
It's confirmed because we got the date.
Okay.
Maybe we organize a.
Great, you can see. But yeah.
If you change that they are not used to bucket sports, I think that's fine. But if you want to play more competitively, then that's it.
Yeah,
Yeah, sorry.
A lot of people on there.
So maybe we wait a bit. I mean, we have plenty of time. From our side, it's fine.
You're not filling your.
Oh, yeah, I think we're good. Bubble that we might be interested in, so reconstructing capability reasoning, protocol reasoning, has all the like rate limiting and a bunch of this other like seemingly unrelated, totally unrelated stuff as a using some structural logics.
Okay, that sounds super interesting.
Yes, it actually cites one of our examples cites your paper with Tobias on linear capabilities.
Ah, right. So all the more reason to. You want to send me a last?
Yes, yeah, I get it. Actually, one thing of revisions, but so also be the company.
Notice when you added math contents to the record. But there's and suddenly someone was telling me, like, One is giving this so interesting talk, and I was like, oh yeah, that sounds really interesting. Where is it? Yeah. Make you feel stupid.
Yeah, she finally went like the.
Yeah, no, that's good. Yeah.
Did you go in? Yeah. Okay. So you
Bueno. Y no sabemos nada todavía del.
No, todo lo que me dijeron es que va a ser este mes, así que puede ser que ya lo eligieron, que todavía como que.
Vale, perfecto. Yes, which one do you?
I don't know if it will work. We can try it.
Yeah, so that along the stuff.
Yeah. So that one, next slide, that one, previous slide. That's the point. Good. Yeah, no, don't.
Is it already recording?
Yes.
Well, we're going to start. Hello, everyone. Welcome to the Erlang 2025. This is the 24th ACM6 Erlang workshop, and is co-located with ICFP, as in previous years. The chairs is 12, so people, Alakosh, who couldn't come, and Laura, which is this is a forum for presenting research and experience reports about techniques, tools, languages, and novel applications, and it's focused mainly on being languages. What this means is that it's focused on concurrency, parallelism, distributed programming, actor modeling, and so on. There's a lot of emphasis as well on functional programming, concurrency, and reliability, as you will see from the presentations that we have today. We received 8 submissions, and each one was reviewed by 3 program committee members. 5 papers were accepted, 3 were rejected,
We also have a space for lightning talks, where we will see upcoming work from industry, I think, and also from academia. This is the schedule. So we start with Tobias as instructor. Tobias will present a keynote, followed by a coffee break. Then we continue with formal semantics and verification session, which will have a bit of mechanized proofs in Erlang, deriving an Erlang interpreter from mechanized formal semantics of core Erlang, and a lightning talk called the State of the Union challenges for checking unions and generics and that whatnot. We continue with another session afterwards, which is about tool systems and static analysis. There will be a talk about the stop the world debugger for Erlang, followed by evaluation of Atom VM for Erlang fault tolerant ERP32 based systems, and a lightning talk about Mailboxer given by Laura. Followed by a coffee break, and we finish with distributed behavior. So we have a talk about moving objects and behavior cycling ad hoc networks, lightning talk about I'm going to pronounce it Devon, a monitoring tool for distributed deadlock detection, and a final lightning talk about securing Erlang and Elixir applications by Melina. And then we finish with the closing remarks. The program committee consisted of Cons from Meta, Stavros from Erlang Solutions, or industrial companies, Bete, which is here, thank you, Victoria Fierdos, Paul Harvey, I'm going to say Sabak, Chaba, thank you, Daniel
Horpachu.
That's what Isabel one, Stanley and then thank you to Italia. And the Supreme Committee takes a set that I'm not going to read for the pronunciation. And we're really grateful for the support that our sponsors, from our sponsors like the Erlang Ecosystem Foundation, Ericsson, Erlang Solutions, and Ashland. Without them, we would not be able to give stipends to people who come and present work I'm going to present today. We would like to thank you all for participants and the larger community. So thank you all. All of these are languages that run on the Beam virtual machine. So that's Erlang, Elixir, Lisp, Clever Erlang, Glean, Caramel, Fika, Clojure, Handler, Alchemy, OCT, PCL, Lua, and Brave. Great languages. And now we're going to continue with Tobias' keynote. So Tobias is full professor at Uppsala University, and he's going to talk about the challenges or introducing the concurrency in Matter. Thank you so much.
Thank you, Hiko. Right. Yeah, please start. Okay. Oh, no. All right. Hello, everyone. So I will be talking to you about something that we internally refer to as Erlang. So it's sort of, if you can believe it, it's the best bits of Python and the best bits of Erlang combined. So we'll see a little bit what that means later. I mean, I'm guessing that maybe some people in the group think that's zero Python and all of Erlang, but no, it's Python is a weird and wonderful language, and you can do a lot with it. And we're trying to sort of facilitate doing more. Right? So this is joint work with a bunch of people that I will try and point out as I go along. Okay, right. So, no, interesting. Let me make sure that the clicker works before we continue. I think by agreeing to present Hiko's slides as well from the laptop, I should have done that. Did it work now? Yes, great.
Now, right, so let's start with a little bit of background. Right, so we're going to be talking about Python code today, and most of you can probably read this fine, even if you've not seen it before, because it essentially is pseudocode turned into a programming language, so it's very, very nice. And right, so this is like a very sketchy Mickey Mouse program to build some kind of small server skeleton application. We have when this program starts, it's going to define a function called do work, right? And then we're going to create a socket, and we're going to a while loop where we're listening to connections on this socket, right? And then once someone actually tries to make a connection with us, we'll call the do work function and perform some work, right? And once we're done with that, we're going to be returning back into the while loop, as you can see, which never finishes in this case, and then keep listening for the next connection. And when that comes along, we're going to call do work and do a bit more work. When we're done, we fall back again, and so on and so forth, right? So this is just to get you familiarized, mostly with my voice actually, but also with a little bit of Python. Right? Of course, no one is very likely to write a program like this. So keeping on with this sort of skeleton, sketchy program tradition, why don't we break this up into some asynchronous tasks instead, right? So whenever we have a connection coming in, we create a new thread, which is of course fairly heavyweight, but fits on the slide, to perform the work of the do work function in a task of its own, right? And in that way, we immediately can go back to listening on the next connection and serving all of these requests in parallel, right? Or at least so you'd think, right? But in reality, this is not the way a Python program executes, right? The way a Python program executes is this. So it's basically taking all of these tasks and running them interleaved on one single core. So Python is concurrent, yes, but Python does not offer parallelism, right? We cannot run multiple tasks in parallel at the same time. So if we try and do this little experiment where we make 100 million independent calculations and we split the work over one core, two cores, one thread, two threads, 4 threads and 8 threads, and we look at the time it takes to run this program, well, it's exactly the same regardless of how many threads we use. And it's exactly the same amount of CPU used regardless of how many threads we use, because it doesn't do parallelism, right? And so this talk, the context of this talk is really like, how do we get from this way of running Python to this other way of running Python? So like, what's the problem here? Well, the main obstacle is really this thing called the global interpreter lock. Right? So the global interpreter lock says that only one thread at a time is allowed to execute a bytecode in a Python program. So even if we have multiple tasks, and even if we can schedule these tasks across multiple cores, there will only fit one inside of the box at a time to execute a bytecode. So we are going to serialize this execution nonetheless. Right? So why is that? Well, we have to look at history a little bit to see how the Python got its scale, right? So basically, the global interpreter lock has been around since the dawn of time in Python, and for a long time that was a really nice design, right? We used to be able to every year throw a bunch of more transistors at cores, making a single CPU go faster and faster, and then we hit the power wall around 2005, and then it turned out, oh, shit, we can't keep doing this anymore. We need to figure out a better way to use the transistors that we have. And that was the rise of multi-core computing, right? Then we started seeing computers with more and more cores. Right? So basically, at the same time as the clock speed increases, peter out, we're seeing an increase of the number of cores that we have on our chips. So that's roughly around 2005. And at that point in time, Python is around 2.3 to 4 version, right? So there's like a lot of stuff building on this global interpreter lock-based design that's been around since very early in Python's history, right? So how many in the room know when Erlang made this transition?
right? So Erlang was in the same tent, right? In 2005, Erlang also was not parallel, it was concurrent. So when did Erlang become parallel? Kiko, you should know this, you work with it. Right. So it's 2006, right? So essentially, immediately when industry starts transitioning from single core computing to multi-core computing, Erlang changes and adapts. And that's what you'd expect, right? It's a concurrent language is built for this. The design is perfect. And Python is now 20 years later still sort of struggling to make the same transition. And that's the context for this talk. All right. Please stop me at any time with questions, or if you want to heckle me or whatever, so we can make this a bit more interactive if you like. All right, so I'm going to go back to the global interpreter lock. Right, so it's fundamental for some things, predominantly how Python deals with automatic memory management. So I will now go a little bit into how memory management works in Python. And we are soon, as we've sort of learned how that works, going to look at a little example where we have multiple cores trying to assign, multiple threads trying to assign to local variables from the same shared object. Right, so reference counting, that's how Python manages most of its memory. Right, so the way this works, right, is if you create a new object, in this case, we're creating a new person object and we're giving it a name, which is just a string, then we'll get an object, a reference from that object to the string, and a local variable with a reference from the local variable to the object. And the object and the string will both get this reference count, which is basically a counter that shows what's the in degree of reference coming into this object. Right? In this case, the reference count is both 1 for both the string and the person object. Right? And if someone then comes and assigns a new value to the local variable, then of course this reference is going to fall off. Reference count decreases to 0. This happens automatically in the Python language. And then we can delete the object. And when the object is deleted, then of course the reference to the string also goes out of scope. That means that the reference count goes down to 0 when the string is deallocated. So this is sort of bread and butter stuff. If you haven't thought about this stuff for a long time, now you hopefully swapped it back into memory again. Right? So that's how reference counting works in Python. Of course, things aren't just that simple, right? Because if we imagine we're creating the person object again with the same setup as before, and then let's create the second person object. And why don't we take these two objects and they marry each other? So now we have this nice spousal relationship. So we have now a cycle between these two objects, right? And then if the program is done with me and my wife in this case, right? So so we drop the reference count for Y and we drop the reference count for X. Then sadly, still like poetically, as it were, like me and my wife are still clinging on to each other somehow, and then the reference count is still 1, even though the program can't do anything because the program has no way of getting to these objects. The reference count is still not 0, so they did not get deleted. So on top of this reference counting scheme that Python uses for memory management, it also has something called cycle detection. So that's basically a tracing-based garbage collector. All of the objects, they participate in this doubly linked list that you occasionally walk and use to find cycles in your object graph. So essentially what will happen in this case is the cycle detector is going to pretend that these two references across these two objects did not exist and say, oh, if I remove them, what would the reference count be, right? To essentially figure out, like, is this an isolated component? And if the reference count then drops to 0, which it will because there are no incoming references from the stack, then we've found a cycle and we can remove these objects, right? So we have reference counting and we have cycle detection, and the global interpreter lock is essential for both of these things. And let me show you how. So I'm just going to focus on reference counting for now. So we're back to the case where Z is a local variable pointing to a person object again. And we're just going to assign from Z to X in one thread and from Z to Y in another thread. All right, so basically we're going to this situation up here. Right, so if we look at what these assignment statements really were, like mean under the hood, it's something along this line, right? So we'll start by reading the reference count of Z, and then bumping the reference count's value and writing it back into Z, then storing the old value of X in some temporary variable. Now the assignment actually happens. And then we do the manipulation of reference count of X, because we just overwrote the reference to X. So we need to decrease its reference count by 1. And if we hit 0, then we want to deallocate it, something like that. Right? And this happens, of course, in both threads at the same time. And when we have the global interpreter lock, then all of this stuff fits inside of the box. Right? So there will, like, this will appear atomically to the rest of the system, which is a nice property. But of course, if we were to remove this global interpreter lock because we wanted things to become more parallel, then all of these things can happen at the same time. And now things start to become tricky, right? So let's just focus on these first 3 lines of each thread, right? So it's really this operation, right? Bumping the reference count that we need to worry about, right? So it's really, again, these 3 different things, right? Read the old value, increase the old value, and write it back again to wherever we got it from in the first place, right? So if we have a bunch of threads trying to do this at the same time, and we're still in this world where we're protected by the global interpreter lock, then we'll have both threads competing for the lock. Maybe thread 1 wins this race. It'll then read the current reference count, bump it, it'll write it back, and everything is fine, right? Then it'll release the lock. And then maybe they're competing again. Maybe thread 2 wins this time. It's going to read the updated value, bump it, and write it back, and everything is fine. Right. So, right. Let's now see what happens if we remove the locks. Right. So with the locks, we can, for example, end up with this situation where we have both of the threads at the same time reading the old value, bumping it, and writing it back. Right. So this is your classic database kind of situation, right? We can all see that we performed 2 increases in the 2 different threads, but they were from the same starting value. And then we're writing the same number back. So now we've just destroyed the correctness of the reference count of this object, which means that at some point we are likely to deallocate this object before the program thinks it's done with it, which would really, create some kind of use after free or whatever kind of error would happen. So this is not a good program. This is a program whose behavior is really defined by stuff that's happening outside of the program itself. Right? So we don't really know what this program means, so to speak. Right? And if we want to remove this global interpreter lock, then these are the kinds of situations that we'll need to deal with all over the place in the Python codebase. Right. So that brings me to the next chapter of this story, which is titled Sub-interpreters. So Python is now pursuing 2 parallel ways, no pun intended, of becoming parallel. So we have, on the one side, we have this thing called free-threaded Python. That's spearheaded by Sam Gross and his team at Meta. And they are doing this very heavy lifting where they are removing the global interpreter lock from the Python codebase. So that means going into a lot of places in the codebase, because as you can imagine, this happens all over the place, and changing how Python works. So for example, we'll need to go to using some form of atomic reference counting for memory management. That's really not enough. There's sort of a lot of other heavy lifting that needs to go with it as well. For example, if you're interacting with a list or a dictionary, which are like core object types that Python has, you would like for the list not to change its length while you are operating on it. Right? If I'm trying to take item 5 and then the list has shrunk by the time I get around to accessing that place in memory, that's not good. But that's like another thing that the global interpreter lock does. Welcome.
We're not going to talk about figures 3, are we?
And right, so that's another thing that the global interpreter lock will give you, right? It will give you a guarantee that the list, for example, in this case, will not change afterwards. So if free-threaded Python, when and if it materializes, we'll have parallelism in Python,
which will be memory safe in the sense that the Python virtual machine is not going to crash if you have a poorly synchronized program, but you now have data races in your programming model in a way that previously you did not have in Python. And as you're probably all aware, right, there's a lot of people programming in Python, and a lot of them do not have sort of formal CS training. So this is like a very new and alien concept to a lot of people that is now coming into the language in a big way, provided that also people start to opt into using parallelism in Python. I mean, currently most programs are single-threaded because, yeah, of stuff we talked about before. Right. The other thing, and this is really where I'm going to continue on this talk, is this notion of multiple sub-interpreters. So from Python 3.12, you have the ability of running multiple bytecode interpreters inside of the same process. So really this sort of started off as a hack where you have lots of Python VMs running on the same machine, talking to each other through some IPC mechanism or whatever. And then, okay, this is like a way to scale Python up that's very crude. At least can we bring all of these interpreters into the same process? So now we have lots of interpreters running inside of the same process space that are isolated from each other because they are communicating by copy. Basically, this should be familiar to people in this room, right? So this is a nice way of very sort of quickly getting to some amount of parallelism, right? So you don't have to change the interpreter. The interpreter still has a global interpreter log, but each interpreter has a separate global interpreter log, so you can have as much parallelism as you have interpreters in your system. And because you're communicating using this synchronization protocol, they're data race free and isolated from each other. So that's like a nice programming model, but it's of course a little bit more heavy than just having threads freely sharing memory. Right? So most of the things I'm going to talk about is compatible with both free-threaded Python and multiple sub-interpreters, but it makes more sense, or maybe it's more useful in this context in terms of giving you new abilities. So that's the sort of approach I'm focusing on in this talk, right? So I just want to stress that the reason for this isolation is very pragmatic. It's not necessarily in order to give users data race freedom. It's because, again, of this global interpreter lock. Like, it wouldn't work if you just wanted to willy-nilly share objects across sub-interpreters, right? Because if you imagine that you have this situation where you have one sub-interpreter with one heap, another sub-interpreter with another heap, and then some object that was shared between them, right? Any access on this object from this first sub-interpreter is going to be synchronized using its global interpreter lock. And the other sub-interpreter is using another lock. So they're competing on different locks. There will never be any competition, and we can still have the data races on this shared object. So sharing stuff in this way doesn't work unless you make these objects immortal. What does that mean? It's basically you give it a reference count value which is special, which means, oh, don't bother, right? If you see this reference count value, don't decrease it, don't increase it. This is an object that will stay alive for the duration of the program, right? So basically, if we turn off memory management for these objects, then we can still have some modicum of sharing. But actually, it's even worse than that, because you still have the cycle detection running here, which thinks, oh, I'm only going to see objects that I have created. That's part of my heap, and the cycle detector here that thinks I'm only going to see objects that I have created as part of my heap, and now they can meet here, right? That's not what we want. That's at least not the way Python was set up. Right. So I've explained a little bit about background, and I've explained sort of where we're going with this talk. Now I'm going to go a little bit of left field and talk about something else for a second. I'm going to talk to you about Project Verona. So Project Verona is a language project with a bunch of people. Right, I probably should have put James on this list as well, but you can see him up there, so that's fine. You can just turn around and imagine he has this circle around. Okay, so right, so it's a new concurrent programming language built by a bunch of people. That is, we're trying to give you data race freedom, deadlock freedom out of the box. So a bit of flexible memory management thrown on, and also this notion of no unsafe code, that there should be no point of the code where you can sort of escape out of your constraints, where you could destroy any kind of invariant that you had either in the unsafe code or in the safe code, right? So we're sort of putting lots of constraints on ourselves. I'm going to unpack these bits a little bit as I go along, right? And also we're adding a new concurrency model that is called behavior-oriented concurrency. So let me start by going through behavior-oriented concurrency a little bit. And what better way to do that than to talk about how to cook a concurrent omelette. So this is an example due to Matt Johnson and Sophia. Sophia is coming later in the week if you want to talk to her about this kind of stuff. Right, so we're going to do some concurrent cooking. And in this case, we are going to follow a recipe for an omelette that has these components in it. So on the top here, we have what we call resources, right? So these are now ingredients and stuff that we need to cook the omelette. And then we have the activities, the various steps in the recipe in blue on the side, right? So we have the resources and behaviors. And of course, to dice the onion, we're gonna need the onions and the knife. And to chop the pepper, of course, we'll need the pepper and the knife. To beat the eggs, we need the eggs, the whisk and the pan. To grate the cheese, we need the cheese and the grater. And then to cook the omelette, we need all of the prepared ingredients and the pan to cook it in. And so this is sort of a way of looking at this program and looking at what are the resources that each behavior needs in order to run, and trying to figure out how can we schedule these tasks in a good way in this program. And so if you write this program out in behavior and oriented concurrency style, it's going to look a little bit like this, right? So we start off by saying, when I have exclusive access to the cheese and the grater, then I want to grate the cheese, right? And really what's happening here is that we are in program order, sort of creating and spawning a task, and we're sending it into space, and we're saying this task should fire when it has exclusive access to these two resources. Right? So then, once we've created this task, we're going to say to the system, oh, by the way, when I have exclusive access to the onion and the knife, then I want to dice the onions. And when I have exclusive access to the whisk, the pan, and the eggs, I want to beat the eggs. And when I have exclusive access to the pepper and the knife, I want to chop the pepper. And now suddenly we have introduced like a blocking constraint here, right? Because now we have two tasks in the world that both needs access to the knife, and they can't run concurrently in this system. So this second task is gonna have to wait for the first task to be done with the knife. And then finally, we have the cooking of the omelette, right? Which now depends on a lot of things that happened before, right? So we kind of build up this task graph where we have the dependencies encoded through these resources, and that gives us a way of scheduling these tasks, right? And so if we have a dual chef machine that we want to run, or sorry, dual chef kitchen that we want to run this recipe in, right? We could, for example, schedule it like this. So chef 1 is going to dice the onion while chef 2 beats the eggs, right? And then we'll have chef 1 grating the cheese while chef 2 chops the pepper, and then chef 1 goes for a smoke while chef 2 cooks the omelette or something like that.
Yeah, here there is nothing that says that cooking the omelette must come at the end.
This is a very good point. So let me explain that on the next slide. So if we look at this from the perspective of we have these resources and the timeline, then it's really the question like what can execute at which point. So something that happens in behavior-oriented concurrency is that we take the program order or the spawn order very seriously. So because the program was written in this order, and cooking the omelette, the task for cooking the omelette was created last in this case, we know that is going to run after anything that came before it that uses a resource that it also uses. So in this particular case, it is going to run last because it's dependent on all of the other tasks. And because it was spawned last, it is also going to be run last. So basically the program order encodes this in this case. So this is sort of the way that you write this into the system. And this can become a little tricky, especially if you start to nest these tasks, right? Then you have to reason about like this task was created over here and this task was created over here. Is there a relationship in which they run? Can I now reason about like the subtasks that they spawn, that they also ordered in some ways? This can become a little hairy, but it is also fairly expressive. So I think it's a very nice programming model to work with, right? So in this situation, right? So we start by saying, oh, let's create a task for beating the eggs. Let's create a task for dicing the onions, and like we can schedule them like this, right? So this basically means the yellow dots here means this is the resources acquired by the task for dicing the onions, right? And as you can see, right, there is nothing, there's no constraint on scheduling the grating the cheese operation, right? So it could really come before, right? In this dual chef situation, we can only do two things at a time. So I've scheduled, in this case, beating the eggs and dicing the onions, but it could really be, these three are not ordered, right? They can run in any order that the system decides, right? So we could move it up, sort of. So, right, so by scheduling things, scheduling tasks that operate on the same resource in sequence, we have a guarantee that tasks operating on the same resource will not conflict with each other, they will not race. But a more interesting, or not the more interesting question, but an equally interesting question is, how can we reason about concurrent tasks and whether these two tasks, right, the purple one and the orange one, even though they're not using the same resources, how can we make sure that the resources are properly isolated from each other, that they actually don't race on stuff that is sort of hidden inside of the resources?
Can I be annoying?
Yes.
Are we worrying, whenever you talk about freedom, you've got to talk about what is it, deadlock or something?
Yes. So I in order to fit in the 75 minutes, I cut the deadlock freedom bit, but really, this system is also deadlock free. And the reason why it is deadlock free is because the operation for acquiring all of these resources happens atomically in the system. So you have deadlock freedom falling out how the system works. If anyone is interested, I can walk you through how that's implemented later. But now I'm just going to state it has deadlock freedom, and
So it's not hold and wait.
Sorry?
There's no hold and wait.
Yeah. Right. So let's talk very briefly about resource isolation. Now you're here, James. So let's touch at least some form of eventual consistency. Good. So right. So we are building on a static type system that's called Regio, which essentially takes your heap and it carves it up into these isolated components. So inside of each one of these resources, we call these regions. So inside of a region, you can have any topology between the objects that you like. You can have cycles or double-linked lists or whatever. What you can't have is a normal reference that starts in one region and ends in another region. So that is something that this system will not let you do, and it will catch any attempt of creating this reference statically, and the program will be rejected, right? So you can't have that one. What you can have is this one, right? So you can have any number of pointers coming into the resources, basically like this little hat here or the cone on top of each resource. Why is that? Well, these blue references, they have a different type in the type system. They're saying, oh, I am a pointer to a resource. If you want to get access to the stuff that's inside of the resource, you need to use me in one of these when constructs, right? So you basically, the only way to dereference a pointer like that is to take that pointer, stick into a task, send the task into the space, and then, you'll have to trust that the system schedules this task at the point in time when there's nothing else running that's operating on the same resources as this one, right? So this is kind of similar in many ways to actor isolation, right? There's a lot of connections between actor semantics and behavior-oriented concurrency semantics. And Luke Cheeseman, who did his PhD at Imperial College on this, he was last week at the Gulfest or Gulaga in Chicago, and talking about how we can recover some of the actor semantics from
from this model. So there's a nice paper there if you want to understand more formally how behavioral concurrency relates to actors. Right, so yes, so we have scheduling helping us to make sure that tasks that do not that use the same resource are not co-scheduled, and then we have the type system that makes sure that different resources do not overlap, right? And these are some of the core components now in this Verona programming language, right? So we're using the regio regions for isolation, and because we have these isolated regions, we can also manage memory differently in the different regions. So we can have one region where we use reference counting, and another region that we use some kind of tracing GC, and other regions where we may not want to do any GC at all because like the stuff is going to be alive for the duration of the region, and then let's just torch the entire region when we're done with it. Right, and I guess Erlang has all of these modes of operating too, in a sense, right? I think it's a very common pattern to allocate stuff in an actor and then destroy the actor when you're done with it. So that's very similar to the arena allocation. You have reference counting for big objects, I believe, and then it's tracing for the rest. So this is like we're not breaking new ground in some sense, but I guess here it's the programmer that decides when you use each and every one of these systems. Right, and then we're using behavior-related concurrency for the concurrency model, which is then data is free and deadlock free. So it finally appeared on the slide, even though I did not explain why. Right, and it's pretty straightforward to express different schedules because this program order stuff that we mentioned briefly helps you to kind of reason about the order in which tasks run. Right, so this is a language that we've been working on for quite some time. And we keep getting sidetracked, and the last sidetrack was due to this completely nerd sniping question from Mats Torgersson. So there was a meeting where there were some Python people and some Java people and some Verona people. And as you may know, Java has recently moved to a model where you have lightweight threads, so-called fibers. So this Project Loom, right? And Python was trying to get from like not parallel to becoming parallel. And then Mats had this really interesting question like, it looks like the Python folk are trying to get to the point, to the place from which the Java folks are trying to leave. Like, what would it look like if they skipped ahead to where the Verona folk are? Right? And that was a really interesting question. And so Verona, the programming language, is super interesting. Like one of the reasons why we try to build a language is because we want to understand how all of these components work together. And like what better way of understanding that than actually building a language and testing it out. But even if I was able to snap my fingers now and have the Verona compiler and runtime all finished, what would I have? I would have a programming language with 0 users, right? That no one asked for. But if I could get some of this stuff into Python, I would have a language with lots of users that we could learn a lot from their sort of interaction with these concepts that we're trying to build. So it's really an interesting proposal to try and get some of these ideas into Python to understand better sort of how they work, where they don't work. So we started working on this, and it's really been sort of something that's swallowed all of the members of this project, more or less, and they are now all working on what we call Pyrona instead. So the Pyrona project is trying to take ideas out of Verona and put it into Python. And so what's happening there? Well, we're taking, for example, this regio type system, we're moving it into Python. The Python is only optionally statically typed. Right? So now we have the dynamic equivalent of the type checking. So we have this dynamic region ownership for concurrency safety. This is a PLDI paper from earlier this year that you can read on sort of how we are going to solve the type system issues. And then we're adding immutability, which is something I'm going to talk about shortly. And we want to build behavioral concurrency as a library that uses all of these things. So we're sort of keeping most of the good stuff from Verona, not so much of the memory management bits, but all of the other sort of more high-level bits are in there. Right. And so Python's been around, right, for some 35 years or so. And this is a pretty big thing to do in a language that's been around for that long. So we're trying to get there piecemeal. So one stepping stone to getting there is what we call Erlang. So it's taking the subinterpreters model and adding support for direct sharing of objects between subinterpreters if these objects are deeply immutable. So you have, I mean, we could call this a sort of a poor man's Erlang, if you like, right? I mean, in the sense that the subinterpreters are much more heavyweight than the Erlang processes. You would not spawn new subinterpreters at the same rate as you would spawn Erlang processes. But you could easily, for example, using VOC, build something that uses these subinterpreters to run more lightweight processes on top of them. But we need a way to efficiently share objects between the subinterpreters, and the first step towards doing that is by adding proper support for deeply immutable state. So that brings me to the next bit of this story, which is talking about immutability. Right. So we need a design for immutability that goes with the Python programming language, right? And we have some goals here, right? So, for example, the first goal is the one that I already stated, right? We want for immutable objects to be able to be shared directly across subinterpreters. So that's the first goal. And similar to what I talked about when I talked about free-threaded Python, right? We don't want it to be possible to crash the VM by writing a poorly synchronized program or like misusing immutability. So basically, a programmer mistake should not lead to corrupting the system. Of course, we would like for programmer mistakes to not also corrupt those programs, but that's sort of coming later in this process. Now we're just trying to get immutability to work. And of course, in order to get this into Python, it needs to be sufficiently Pythonic. And we've spent the last 2 years trying to understand what that word means. I don't have an answer, but I'm getting there slowly. Like, how can we build something that can interact with like the value set of the Python programming language? Right, so from these goals, we can derive some key requirements. So the first one is super important, right? It's sort of the like no unsoundness. And I'm guessing to a lot of people in this room, this seems like an obvious design, but this has been an uphill struggle when interfacing with the Python community, right? Because if you have a dynamic language where pretty much everything goes, I mean, it's a super nice and very flexible programming model, but it also leads to like the invention of programming styles that, let's say, many statically typed programming languages opt out of or can't support because they basically cannot express these programming styles as part of their type systems. So we really want a system where immutability gives you a guarantee, right? Because if you don't have this guarantee, we don't have anything that we can build a working solution for memory management on top of. So we like need a sound design for immutability. And this has been a real struggle to convince people that sort of having something that you can't opt out of in any possible way trying to get that into Python is an interesting conversation, right? Because there is sort of, you come back to this idea that, oh, we're all consenting adults here. If I want to violate this property, I'm doing it for a good reason, so I should be allowed, right? And this sort of the, so I'm talking to you as proponents of Erlang, a dynamically typed language. So maybe you'll feel the same as the Python programmers do, but basically a lot of the values in the dynamically typed community seem to be that like if there is a way of like interpreting something that happens as something that the programmer intended, then let's go with it and just see what happens, right? Like if it crashes, it crashes, but if it doesn't, it doesn't. And I'm coming, I will brand myself as like a statically typed person. So that's like the value set where I come from. So I have had a lot of trouble sort of adapting to this way of thinking. But we really need a sound design that you cannot break. Right? Then just like in free-threaded Python, we need some form of atomic reference counting for immutable objects, but only for the immutable objects, because those are the only ones we are going to share. Then we also need
a way to turn mutable objects into immutable objects. And when we do that, then like I opted out of showing some data structures in graph form of Python, but it's really like if you try and look at a Python dictionary and how it looks, it's like has super weird, lots of sharing going on, lots of cycles. There's like lots of things that go on if you unpack the actual complexity of a Python data structure. So we need a way of dealing with cycles, and thus we also need a way to deal with cycle detection. And finally, we need for immutability to be deep. Right? So that begs the question, how do we get this into Python? How can we convince people that this is a good idea? So let's start by talking about deep immutability. So there is a notion of immutability in Python, and it is shallow, meaning it's like I can make this object immutable in the sense that I can't store anything in any of its fields. But those fields can point to other things that can change, right? So that's the notion of shallow immutability. And we need immutability to be deep, right? So let me explain why. So we saw a similar diagram before, right? We have these two sub-interpreters, and now we're sharing these dashed boxes. These are now the immutable objects. And because immutable objects as reference count manipulations happen with atomic instructions, then we don't have a problem with sub one using its GIL and sub 2 using its GIL, right? It will just work, right? Because we're using atomic instructions. They actually don't even need to acquire their own GILs to access to manipulate the reference count of these objects. But if I from one of these objects can follow a reference and get to another object, then if this object was not immutable too, we'd have this problem that we talked about before, basically, right? So I'd have a situation like this. So now it's not immutable anymore. It lives on the heap of subinterpreter 1, and now I have the problem that we're actually using different GILs to synchronize and reference counting, and so we're back in this special place of hell that's reserved for people who write data IC programs, which includes myself. Right. So we need deep immutability. And this is another thing that's tricky, right? If you're interacting with a community that has a notion of immutability which is shallow, and you're now trying to change what that means, it's an uphill struggle. Right. So how do we then design immutability in such a way that we can get into Python the language? Well, right. You can try a purely functional style. Okay. So what would that look like? Well, so now in the purely functional style, we have some objects which are immutable always at creation. This could be like strings, numbers, and things like that. And then, okay, we can build more complicated or complex structures using these simple objects. So there is this notion of shallow immutability, right? And if we just stack shallow immutability correctly on top of each other, we can build deeply immutable things. And this is great, right? Because if immutability is something that's established at the point of creation, then you know what's immutable and what's mutable. It's easy to keep these two words apart. If you want to check if something is immutable, you can just check its type, most likely, and things will work. That's very nice. But it's really not the Pythonic way, and it excludes cycles, and it's really hard to use with a lot of structures that already exist in Python. Right. And so we have this notion of a name the tuple in Python, which is basically a way of constructing data classes that are shallowly immutable. Right? So I can say, oh, I want to have a name tuple, which is called datum, and should have two attributes, foo and bar. So now I get a constructor back for that. And then I can build a Python tuple, which is shallowly immutable, and I can stick two datums in it. Right? And actually, this datum here is fully mutable, right? Because it's built by immutable objects as the leaves, and it is mutable itself. However, the second one has a list in it, and the list is not immutable. So I can take this second datum and I can go into its foo property and I can change it. So something needs to give, right? This does fall out completely for free, and it's not so compatible with just like the notion of immutability that is in Python. right? Another approach would be to build it on some form of annotation system, like const-like annotations, for example. If we take the part of the CC document. And if we did that, then we'd have compile time checking, which would be very nice, right? We would be able to exclude the possibility of runtime errors due to someone trying to mutate the mutable object. And the compiler can help us to figure out where to place these annotations, and that's great, right? But Python is a non-type programming language. All Python code out there is either untyped or is typed using this unsound static type checking that Python has adopted fairly recently, right? So you can have type annotations in Python, but those type annotations are there to kind of help weed out problems, right? They're there as an aid for catching certain programmer bugs, but they don't establish strong guarantees that you can build on. So we can't piggyback on the existing type checking since we need to deliver a strong guarantee in immutability if we want to use this to build like a working reference counting system around. So yeah, we have a problem. We can't just use systems like that in Python straight off the bat. Right, so, but there is more, of course. So here is an interesting thing that may or may not be obvious to you, right? So in this case, I'm creating just a very simple class. It has just one attribute foo. The constructor sets foo, and I have a get method for getting foo. So it should not be a parameter there, it's a typo. And a set method that sets foo, right? And I can create an object called datum from this class, just fine, that's great. But I can also do this, like get me the class and then store to its get foo attribute a completely new function that returns some other value, right? And now if I go back to my datum that I created here with the value 42 and I ask it for its foo value, I get 43 value, right? So I changed really the meaning of that object without touching that object at all by just changing how the class was defined. So yes, this is a problem for us, right? It's not a problem in general, it's a problem for us, right? And the problem for us is that Python's types are mutable, and they are objects too. Every method in a class is also an object. And actually calling a method on an object in Python starts by allocating a new value, which brings together the object and the current, so the function we're calling and the object that we're calling this function on together into a single thing. And then we operate on that object, and then that object dies. So Python has really like a structure at runtime which really resembles, what you'd expect of user data, but the same is true for classes and types as well. So types are mutable, and a lot of Python libraries rely on being able to monkey patch types, right? So you take your type, you send it to some function, and that function changes your type in some way. It inserts some utility or wrappers or whatever, and returns you back the type. So we need to support this if we are trying to be compatible with how a lot of Python programs work, right? Or popular frameworks like Django is not going to work with our immutability. So we need to support mutable types, but of course we also need types to be immutable because otherwise we don't have immutability. So right, the types need to become we need to be able to define types which are mutable, can be monkey patched, and then at some point become immutable. Right, this is getting nasty as you can. So that's approach that's something that we need to solve. So our approach for all of this is just to buy into dynamic checking for everything. So the way we do this is we steal a bit in the object header to track immutability. And then some objects are created with this bit set, like strings and numbers, etc. Other objects you can make immutable by calling freeze on them, right? And because we require immutability to be deep, when you call freeze on an object, that freeze function needs to traverse the entire object graph, right? The transitive closure state reachable from this point on and make stuff immutable. I can see James cringing, and I think you're a beautiful picture of a lot of the Python community at this point. I'm sorry that the camera was not pointed at you. Right. So so we need for freeze to have this sort of spooky action at the distance like property. And it may well be that when you're traversing this object graph, you can find some objects that you can't freeze. There are certain objects that you can't freeze for whatever reason. And then everything needs to fail and back out. So like the freeze operation becomes pretty heavy-handed at this point. So this is nasty, but on the other hand, it's very flexible. Right? It supports this monkey patching. But it buys into this world of hurt in time, like we have now to reason about freeze propagation. What happens if I call freeze in something? Will it freeze something over here that I wouldn't expect it to freeze, for example? And you also get dynamic mutation errors, but I guess that's like just the way dynamically typed languages work, right? So in my code here, for example, I'm again defining the same datum class, and I'm creating an instance, and I can change the instance, and then I can make the instance immutable by calling freeze on it. And note that if I then check, is this class also immutable, it should return true, right? Because the class object is reachable from the instance. So by deep immutability, freezing the instance needs to also freeze the class, right? So that means really that by freezing this instance here, I have now affected the class of any other datum that I have created in my program. Right? Is this good? Well, we can discuss what good means, but this is the sort of the fundamental building block, right? Then you can build good programming practices on top of this. For example, you can create a decorator function that you can slap on a class definition, and that decorator function essentially is something that gets called with the type object as soon as the type object has been created. So you can freeze it immediately. So now we can like build something that looks like type declaration into the programming language that works with this. Of course, not all programs can use that type declaration because they need monkey patching, and we don't know when monkey patching needs to happen. But a lot of Python programs out there are written as if classes were immutable. And we can support them with just the declaration out of the box. Right. So now we're making things immutable dynamically. And now we have these things that we can pass between subinterpreters, and the subinterpreters can reference them directly. So now we need to look at like what objects can or cannot be dynamically frozen. So I'm gonna talk a little bit about when we might fail to freeze. Yes.
Yeah, I'm just wondering if it's not a big problem that this immutability spills to superclasses and to meta classes, because I can imagine that I can make one object
Yes.
frozen and through the class hierarchy.
Yeah, no, that's a super good point, right? So
Like
yes, you are entirely correct, right? So even though datum doesn't have an explicit superclass, it will be inheriting from the object class. And of course, object will get frozen as a side effect of this freeze as well, right? If you interpreted immutability very strictly, you would actually also have to freeze all of the subclasses, because in every Python class, there is a pointer to all of its subclasses. So maybe we would have to follow those as well, right? But we don't. So I think we are trying to find a good place in the design space. So for example, we are not freezing subclasses. You can inherit from a frozen class, even though you have to extend its list, right? So we're sort of permitting some things to stay immutable in an immutable object when we can control that it's properly implemented and that it won't crash if it's used in crazy ways across different subinterpreters. But it's true that we have to propagate upwards, right?
Okay.
So we can't get away from that problem, right? Oh, okay, there are ways of getting away from it. One way would be to say, at this point, when we want to make this object immutable, let's make a copy of the class and make and freeze that class, for example.
Okay.
That is a design that people hate even more, right? Because then you'll have lots of copies and they might have the same, like the type might have the same name, but if it's frozen at different points and monkey patched at different points, and suddenly we have a lot of classes that are all called datum that work slightly differently and were frozen at different times.
An instance of
yeah.
would stop working, I guess.
Sorry?
Instance of would stop working, I guess. Or
Well, yeah,
patching, for example.
indeed. I phrase it as like we'd have to rethink how instance of is implemented, but yes, for sure. If you just wanted to keep on using the same definition of instance of, that would not work at all in that case, right? So that's a path we're not taking. So I'm trying to describe like some of the rejected alternatives, but there are way more that we have rejected in the last 2 years than I can fit into this talk. But yes, yes. All right. So let's talk about freezing functions, right? So when is the function safe to share, right? So this is a pretty common situation in your Python program, right? You have some function, and that function captures some state externally, right? Like if I now freeze this map, right? This is now, this is data that's created inside of the current subinterpreter that's executing. Now I'm freezing this function and I want to send it off to another subinterpreter. Will this work? Right? Do we support this? And these are the kinds of questions that we have to figure out, right? And the way we have decided to make this work is that, yeah, sure, we'll let this work. How will we do that? Well, we'll do that by sort of following this pointer, finding the list and making the list immutable, right? That's the freeze propagation problem again, right? So we're buying into that design. So that means you can freeze this thing. You can call it as long as you are not doing anything like this. This function is not doing any mutation on the external state. So you can call it just fine. But if you try to append to foo, right, that's going to now fail because we're assuming that foo, we're imposing that foo gets immutable because we're sharing stuff, or at least we're setting things up for sharing across subinterpreters. So similar situation, we can freeze this one as well. It has exactly the same kind of structure, right? And now it can become even more complicated because sometimes when I call it with some values, it doesn't go into the point where you do the mutation. So this one works, but if you call it with say 4, it's going to fail because we made the list immutable and you can't append to it. And these can be tricky things to debug, right? Because we have function abstraction, we don't know exactly how say this is implemented. Right? Of course, it's easy to stare at bad code and say, oh, this is ugly. But the key is like figuring out what are the programming patterns that that Python programmers should follow in order to not create these kinds of situations, right? Right. Similar thing again, but now it's even worse because this inner function is capturing the reference to the outer function, which now lives somewhere on some stack frame that we promoted to memory. So it might even be that there is no variable to look at to find the thing that we have frozen at all, right? So again, you can freeze that one, but if you try and call say now, it's not going to work because we made this value. Right, here's a more interesting case, right? So typical Python program. Let's import logger and then use logger.log inside of some function. Can we freeze this one? No, we cannot. Well, we can, but we've decided that we won't. Why is that? Well, it's because this one captures the module, right? If you freeze the module, a module in Python can have any amount of state, right? And you can have classes, and the classes have state as well. So, like the propagation of freezing this type would be too hard to deal with. So in this case, logger is a type. The module is a type that we won't permit freezing. So this case is going to fail. It's going to fail dynamically when you try to freeze it because we can't freeze logger. So we don't permit that. Right? So, right. So we have this problem of captured external state and module state. Right? So this actually works. Right? So in this case, we've just moved the import statement into the decorate function. That works. Okay. Why does that work? Well, it's because we're freezing this thing, we're sending it off to another interpreter, and now we're running import the logger in that interpreter. So we're getting that interpreter's logger. Right? So that's nice, right? Is it just nice? Well, it's not necessarily just nice, right? Because if you remember, every interpreter has its own isolated state. So unless the logger was written in a way where you can have multiple interpreters importing it and it still works, this couldn't be bad, right? But Python is coming up with some notion of, I think it's called a multi-phase initialization module. So these are modules that are supposed to work, even if you import them across multiple interpreters in different ways. So some support is coming into Python, sort of unrelated to what we are doing, that should make this simpler. Right? So you can freeze it, you can send it, and you can call it, and it works. Right. And now another fun fact. Right. So again, I have x equals 42. I have a method that captures x. I freeze foo. Right. If I call foo, it returns 42. That's fine. We permit this, so you can reassign x to some other value. If we print x, gives us 4711. If we call foo, still returns 42. So what happens in Python is that Python is creating internally inside of the function object something that it calls a cell, which is something that's pointing to the value of this variable. In certain cases, the cell will be the same cell as the external object. In some cases, it will be different. We're making sure that it's always different, and so that if you freeze a function, you are freezing the value, but you're not preventing this external variable from being reassigned. And this is particularly good when you have like lots of global variables, which Python programs are full of. Right. So let's talk a little bit about pushback, right? So some feedback from the Python community. I've already talked about the first one, and in the interest of time, I'm going to move on. But there's been a lot of issues about like, why do you really need to enforce your properties? Can't we just like all get along? And that would be nice, but we need something to build the implementation. Right? To my surprise, we got a lot of feedback from these Python proponents of static typing. Like, how this is weird, right? Because if I define a function and I give it an optional static type of saying this is a list of ints, I expect to be able to append to it. But now the list can actually be mutable, so I can't append to it. Some other type system is lying to me. I don't like this. And then I think this is a fair point, but it's also the case that there is nothing that guarantees that x.append 42 will work even in Python today for this type, right? Because this is not a strict type system, so it could fail in any number of ways. But we're just adding more ways in which it can fail. It would be super nice to add support for immutability to Python's optional static typing, but that's sort of down the road. That's not. I don't want that on the critical path of this stuff. And then finally, the big pushback is like, how do we reason about or limit freeze propagation, right? So I have some list. Now I'm calling a function, and then can I trust the list to still be mutable when this function returns, right? Essentially, people are afraid of other programmers sticking calls to freeze into arbitrary places and thus messing up programs. Same thing here, right? I have a function, it takes 2 arguments. I freeze the first one. Will it affect the second one? Right? I need to reason about whether these structures overlap. So what's our answer here? Well, so we're trying to deliver immutability into Python in stages. And this is not so much stages in the sense of like, let's make different stages for different Python releases, but rather a way of explaining what kind of functionality, I'll turn that around. What kind of complexity buys you what kind of functionality, right? Which is a super important argument to make, I think, to a team of core committers. So Python already today has some notion of inherent immutability, right? So there are like numbers and strings, for example. They are objects that are immutable, and their types are also immutable. So they are actually deeply immutable in our sense, just that like the way Python is set up today, it does not allow sharing numbers and strings across other interpreters. Tuples and named tuples. The tuple type is immutable. The named tuple type is also immutable, but they are only deeply immutable if we only put other deeply immutable things in them. So we could build something that only leverages the stuff that is already immutable in Python. And really the key here is like a lot of these types are already effectively immutable. So we can put this into Python without having to go through this, like freezing the type and having that propagated. And then we can give you some small modicum of immutability with this, right? So this is great, right? We get back to this nice property that we had when I was talking about the design of immutability from a functional programming perspective, right? Like immutability is defined at creation time. There's no call to freeze anywhere. It's like I've created something, it's immutable, and it's done. It's easy to reason about what's immutable or not. What I need is this frozen check. Basically needs to traverse, do the same thing as freeze in the opposite, right? Freeze would be turning things immutable, but is frozen now needs to check, are they immutable? And then we could possibly cache the result if we like, if we don't want to walk structures multiple times. So this gives you like a little bit of immutability, but not a lot. But it's like you could build some fairly interesting programs that exchange data in named tuples. So not too bad, but it doesn't support user-defined types, and that's what's coming next, right? Support for user-defined types. And now the main challenge is really the one that I already talked about, right? Mutability of types and monkey patching. So, right, that's the main challenge there. And our solution, the best one that we have so far, and I think the one we will be sticking with, is to add this freeze function. So you delay the time at which something becomes immutability to some arbitrary time in the future. But if you know you're defining an immutable class, you can just, for example, slab a decorator on top of the class and having it be frozen immediately after it was declared. A lot of people write their Python programs like that, so I expect that to work most of the cases, but not in all. Right? And then, of course, the new main challenge with having a freeze function is dealing with freeze propagation. And our solution that we have here is a notion of self-containedness. So basically what we want is to say, when you're freezing something, that's going to succeed, or no, I'll turn it around. This is going to fail if we find that there are pointers into the structure that you're freezing that are also not in the stuff that you are freezing that will be able to witness this change from mutable to immutable. So let me unpack that slightly. Right? So let's say I have a stack frame with variables x and y, and here are some objects. If I try and call freeze on x, right? So that would freeze this one, and this one, and this one. This is going to fail. It's going to fail the self-containedness check because there is a reference from the stack frame to C that will be able to witness that we froze this underfoot. Right? So this is going to fail. And similarly, freezing y is going to fail, and it's going to fail because of this reference. Right? This other structure is going to have its C object frozen underfoot in a way that might be confusing. So that's also going to fail. However, you could do this, freeze x and y. And that's going to work because now we have sort of mentioned all of the places where we're expecting to see this change. So that's fine. But I'm actually lying to you a little because this will also work, right? It's really about the identities of the objects, not the names of the places, right? So essentially, if you know that you have two incoming pointers here, you can write it like this. If you expect there is another incoming pointer from somewhere else, you can just mention that object once again here and we will freeze it, right? So there is like, this is not a perfect design, but someone who knows the data structure intimately can still write something that will allow you to freeze it. Of course, that can be misused, but then we get to use the consenting adults sign on our side of this equation and say, well, yeah, but that's sometimes how it goes, right? You should be able to do that, right? So this will work. So some consequences of this self-containedness requirement, right? So for example, we go back to the list that I had as a critique a couple of slides back, right? If I call bar on X, will I still be able to append to it later? Oh, yes, you will, right? Because, so we have the stack frame in main, pointing to the list, we have the stack frame in bar, it's pointing to the list. So if bar calls freeze on X, it's gonna fail, right? Because it's not self-contained, there's a pointer coming into it from the stack frame below. So that's not gonna work. I think, do I have an animation here? Yes, I do, right? So same thing here, this will also fail for the same reason, right? If X and Y overlap, we don't succeed in the self-containedness check. So this will also work. Basically, if this line did not throw a freeze exception, then this is going to work, right? So if you wrote your program with a working freeze there, then y.append 42 is still going to work. So if you create a class, you create an instance of that class, and you want to freeze the instance, that's going to fail. Why is it going to fail? Well, again, it's the self-containedness check, right? So we really have a reference from the stack frame to datum and to the datum instance, right? So trying to freeze this one is going to basically confuse this reference, right? So you'll have to do D or datum at the same time. And this is again why like having a decorator solution is good, right? Because it's going to freeze the object before freeze the type before the first instance has been created. So that's really nice, right? But right, it also means this, right? If someone calls bar, then bar won't be able to freeze X. It will never be able to freeze X because it's going to be an alias to X on the call in stack frame, right? So it's never going to succeed the self-containedness check. So we just made making objects immutable a lot harder. But in some sense, you could turn this around and say we're imposing that you find some principles that you use to deal with immutability, right? You can't just insert these freeze calls willy-nilly. And that's in some extent good, right? And of course, you could do something like this. We could add a move instruction to Python. So we remove the X on the call site and move it into Bast, right? Sort of linearity style. This will be hell, of course, in a dynamically typed language, but you could certainly, James is saying it's not going to be hell?
No, of course not.
Okay, cool.
So small talkers will probably know it as become.
Right. But I didn't add this, can you unpack the reference here, James? Why is this emoji full of lather?
Well, you know, if you do that kind of thing.
It's slippery, right?
Yeah.
This is the old Boylan constraint. It's going to be hard to figure out who owns X, right? If I call a function on something and then X suddenly vanishes, then I need to return it, right? I need to chain it through my entire program. This becomes
Well, there are things you can do to make it easy, but you probably don't want to do them.
Come in?
There are things you can do to make it easy.
Yeah.
You probably don't want to do them.
Let's talk offline. Right. So and then the third and final stage is basically unlocking more freeze propagation. So taking a leaf out of the Python design book, this is sort of a common pattern that you have some double underscore field in an object that means something, right? So in this case, we have double underscore freezable, or in Python parlance, this would be dunder freezable. So dunder freezable equals true means that this object can be made immutable even though there are other incoming aliases. So we're basically opting out of the self-containedness check. And now we can deliver lots of nice ways of getting dunder freezable equals true into the language, right? So for example, we can have these kind of decorators that will make sure this guy here, whatever X happens to point to, at the point where freezing foo will become dunder freezable. We are building in some notion of a pre-freeze hook that we, like whenever we are trying to freeze an instance of foo, we're first going to run the pre-freeze hook, and that has the option of setting dunder freezable in the crucial places. So you can build data structures where you opt in to supporting freeze propagation without the strong self-containers requirement. Right. In the interest of time, I think I have 15 more minutes. Is that correct, or am I misinformed? I have 1 more.
Yeah, 3 more minutes.
3 more minutes. Oh, interesting. Okay. So then that's a lot less than 15. Okay, let me just briefly then say something about escape hatches. So classic question, right? What if I have an instance counter in my class, right? And the class now became immutable. So I can't write these classes anymore. So we are providing different escape hatches for this. So we have fields that you can have in your class that can contain immutable objects that stay immutable. That's one way. Another way is to have something that basically proxies stuff back to the interpreter from which you came. So this is similar to thread local data. Right. So so let's just briefly talk about implementation stuff in the last minute. Right, so getting this into the CPython code base is interesting, right? Because we have to implement immutability as a write barrier, and there is no single place to put it. So a lot of the problems here is like finding all of the places where we need to insert basically this C code and then propagate the error to the right place. So right now, the most feature development branch has 146 calls to this checking function. But there may be other places that we haven't discovered yet. So just sort of finding them and figuring out if they've been implemented correctly, that's really the key. Right. Let me just spend 1 second on talking about how we collect cyclic immutable garbage without tracing. So when you call freeze on something, we are going to perform a strongly connected component analysis on the object graph. And I'm not going to be able to walk this through, but I'm just going to show you quickly that basically using an SEC algorithm, we are going to find the strongly connected components of all of the object graph that you're freezing. And because all of these objects are now immutable and they reference each other in the strongly connected component way, they will have exactly the same lifetime, which means one single reference count is enough to manage the lifetime of this entire group of objects. And so what we do is we take the reference counts of all of the other objects in a strongly connected component and turn them into essentially pointers that identify where is the single reference count. So if you try to do a reference count manipulation on E, it's going to follow this pointer and atomically manipulate the reference count on A. So now you have cyclic immutable garbage collection with reference counting only and no tracing. So we still have like all of the nice properties that you'd like inside of the implementation, even though we don't use the tracing for cycle detection, which would be unsound as the tracing assumes that it's only operating on objects that it itself has created. So this is my final slide, so don't worry. Right, so this is, as you have seen, there's sort of lots of ideas coming together and then suddenly being thrown into Python land instead of Verona, right? The beauty of working on Python is, of course, that we get all of this interaction with the Python community and pushback and people challenging us on our design. When you're building a programming language at the same time as you're designing all of these things, then you can easily set it up so it becomes easy for you. And whether that's good or bad, we can discuss, but it is certainly very useful to go out of that box. A super interesting thing is all of the stuff we're taking from Python and now moving back into Verona. So we have discovered essentially that the programming model that we can deliver inside of Python
is a lot nicer than the one we were designing for Verona. So now we want to take some of that good stuff back into the Verona language. That's very nice. So to conclude, right, I think if we are successful with this current step, then we will be able, or you will be able, the people programming in Python will be able to share immutable objects directly across sub-interpreters and threads, of course, in free-threaded Python. So that's sort of the stuff that's coming up. And if we manage to deliver that, then we'll go on to the next step. And if we're successful there, then you will be able to write behavior-oriented concurrent programs inside of Python with data risk freedom and deadlock guarantees using this dynamically checked ownership system that we published earlier this year. And I'll stop there. So thanks for your attention. Yes.
I have a question about Verona. You said it's deadlock free because it doesn't have hold and wait. Does this mean that you can't have nested when blocks?
Oh, you can have nested when blocks for sure. Absolutely. Why would nested when blocks not work?
Because I could run when on one resource and then when on another one.
Oh, I see where you're going. Yes. So this is the when syntax is really nice up to a point, and I think we've just crossed that point, right? So I think what you are saying is, like, if I do this when A, comma B, and then in here I do when C,
yes,
right? And I think you are expecting that in here you'll be able to access A and B. That's at least the. Okay.
Or do you like release A and B actually?
Right. So really what happens here, right, is that when we say when A and B, really what's happening here, right, is that we are creating basically we're sort of lifting this into a closure, right? And we're registering this closure with a runtime, and we're saying when we are able to get exclusively hold on A and B, this is when we will call this closure with A and B as arguments, right? And this thing, right? So this when hasn't been created yet, right? It's going to be created when this thing runs, right? And then it's going to spawn this, send the equivalent closure for this one into the void, and saying run this when you can have exclusive access to C. So why would this deadlock?
You could have when C, another one that is when C, and nested when A.
Right. Yes. So that, well.
But you release everything in yield.
Yeah, exactly.
Nested in a when. That's the problem.
Okay.
Yeah.
So there's a question of whether you can have any code between the two curly brackets. Can you write code between the curly brackets, and what's the semantics of? Now further down, the two closed curly brackets.
Here.
Yes, there.
All right. So we have code 1 and code 2. Sorry, what did you say, James?
Are you allowed to write code 2, and what's the semantics of it?
Oh well. So basically, this runs, right. So if I have since we're all computer scientists, I'll add the code 0 up here, right? So I'm running code 0 synchronously. Then I'm running this code synchronously, which just spawns the when, right? Since like this thing may or may not have run yet, we don't know, right? And then I'm running this line. And let's say that this, for kicks, for example, used C as a resource, right? I'll be giving up this resource at this point. So I will have been blocking this from being scheduled, of course, until I'm done with this.
So in fact, all those whens can actually migrate, modulo local assignments can migrate to the end of their enclosing scopes, right?
Yes.
Or go.
Yes,
Yes, if they're holding anything.
There are some details, such as, for example, if you have a bunch of when blocks that are all holding on to one single resource, then we know that they're going to be running in sequence, so we can actually like take some linear data and flow it through them without having to.
But code. The important thing here, I think, is that code 1 does not have access to the lexically enclosing A and B.
Indeed, and this is the thing that's confusing with the syntax, right? Because if you look at this, it looks exactly like a conditional, so you'd expect that in here you'd be able to access anything that's around it, but it's more like a function call where it's a function call where you basically define the body of the function as a use once function in here, right? But basically it does not capture anything in here, so you don't have access to stuff in here and stuff.
Okay, so do I get it correctly that it runs concurrently?
No.
Yeah, if I go back to B, right? So for sure, this thing you spawn the block here, and since it's resource that it needs is C, and this is A and B, it can for sure start to run immediately here. Right? But it can't access A or B, and it can't access anything that's written in code 0 or code 2.
Okay. Okay. Sure.
Right. Yes. And I think this may be a problem that we need to solve, because when you look at it like this, you'd expect to be able to reference things up here, down here, right? And there are multiple ways of thinking about this. One is we should not release this into the world without the proper LSP that will shoot down any attempt of referencing things out here from in here. For example, that's another way of sort of retraining our minds. But I think as programmers, we're all taught to, at least if we use this kind of syntax, to think of this as something where you can access stuff directly from the in-process scope. So whether that is too hard to reprogram or not, I'll get back to you. Yes.
Okay, I have two questions. One is about this. So I guess the way you, in the original example, the omelette is cooked after the egg is being beaten, is by spawning it inside, I guess.
No, so I'm spawning it here, right? So basically, if this is the, like, if these are the two ingredients that I want, right, then I can say when A and B again here, right? And because I spawned this after this, it's a guarantee that the program order will be okay.
Yeah, the question is, what happens when freeze fails? So can you catch an exception and basically to say, freeze, please, this part of this object?
Yes, indeed. So when freeze fails, we will be able to tell you with pretty good precision why it would not succeed, right? Same thing if mutation fails because something is frozen, we can also in the exception that you get then tell you where things were frozen on what line to kind of help you understand like sort of my code right now is not agreeing with code that happened over here, and at least you can find that piece of code and you can try to debug your program.
So is that only for debugging or also for writing code that, for example, treats an object as immutable? So if it's frozen, it's great.
Yeah. You can introspect on an object and ask, is it immutable, is it immutable? And then you can definitely catch the immutability exception and keep going if you like, right? But so that's like my statically typed nature cringes at what you're saying, but you can totally do that, and you may even be right.
No,
I'm just broken in my particular way. Right?
I agree with that.
Yeah.
Interesting.
Can you freeze a foreign object like a NumPy array or something?
Well, yes. I think the short answer is yes. I mean, there are some details, right? A lot of the complexities that I actually did not go into today is like figuring out how does this interplay with C extensions, right? Because a surprising amount of Python code is actually written in C with like a thin layer of Python around it, right? And that's sort of the way the community, for example, has gotten around the global interpreter lock, because if you escape out in C land and you stay in C land, like none of those constraints hold. But there is nothing fundamental that prevents a NumPy array. I mean, NumPy already has immutable arrays, right?
From an example, like for like a decade, I worked on high performance rendering stuff, and so it worked like you said, where it's like a little bit of Python that's driving a lot of C, and all that C is mutable. Do I have to propagate the write barrier into the C structures?
Yes, to some extent. I mean, basically, if you inside of that C code is manipulating external Python objects, then you don't need to do anything. Those objects should protect themselves, so to speak. But in C code, you only really need to ensure that whatever you are doing does not break the memory management aspects of the subinterpreters. So you're pretty free to do whatever you want in your C code. As long as whenever you go out to Python code, you're going to get that check there. If you are implementing, let's say, Python class,
and you have a couple of methods that drop into C and they are implemented in C, then those methods should preferably use this check write check to make sure that they are not like breaking immutability. But you could also like, let's say, start inserting locks in the C land and like get out of the problems that way, right? So you have sort of full flexibility to solve the problem in whatever way you want. I think it all comes back to like, what's your contract with your user, right? Do you want to deliver immutability, or do you just want to enable sharing and sort of piggyback on immutability?
Okay, sorry, let's take the rest of the questions over coffee, and we'll
Sounds like a plan.
be here back at 11. Thank you so much.
Thank you.
Kiko, great to see you. How are you? How are you enjoying the work?
Yeah. That you were. You're not with even
Aggressively against performance.
Good for you.
In a way, yes. It's usable for like a few seconds in the way. Now they publish.
Yeah, I mean, that's certainly one way to do it. We're hoping that they will not stop there, right? Who knows? But I think the stuff we're building, that we want to build on top of this, will not really work with and things you want to run a program, and you want to be able to deploy that, regardless of whether the Python instance is using sub-interpreters. I think our design is actually better because it works the same way across both. Yes, I have done.
So after getting in trouble,
Oh yeah, for sure. Yeah, like you can even mess up isolation without cooking using, right? But you have to really check it out.
Because
Yeah, no, I mean, I think everyone, like it was like a very nice substance, and if you say everything is very, very nice. So that like occasionally there's a library that does some crazy stuff, and now to deal with that propagating
No, so my thought,
we should see
my thought is now, both of them.
I'm trading because
So the first talk, the second talk, I hope to get.
we're not anyway, they would like to see anything along the lines. Yeah, I think there is also like this line share.
I mean, as a practice,
It's pretty similar, right?
those
We don't do
and
but we have the resources.
but most of these actually like so important.
In this then your region in theory they should be sub-interpreters. Then messaging is essentially like that's the substrate that you use to send something from one sub-interpreter to another.
I mean,
Then like allows you to directly share those. To make it
I'm doing it also.
So it's a performance. So there is the message, and you don't really comment on the slide, you don't show at any point the communication we're just talking about. Like if you have communicated,
Okay, so yeah, as well.
and also that's like
Yeah.
That's a whole other little thing.
Like the API for doing that outside of
program.
Python is also changing a little bit. So
Yeah.
this way it became more.
When
But no,
Yes, well,
that's when but I think this has been our way of saying like, oh, if we can get this, then like a lot of programming style that is
big
used
data
in
summarization,
some
yes, I'm aware that say that's sort of knowledge we have both to communicate with
with the community because they can understand what that means. Right? Most of them are not PL people or language designers. So
If you say
like,
keep
getting
finding
into
well,
very
natural language,
complicated arguments
yeah,
about language design is hard to say like, oh, now it's going to work.
Engine will replace program.
Like this thing over
It's
here,
obvious
that you probably are either familiar with or like the X number.
Pre-trained translation engine won't replace
Good message.
program. Pre-trained, it might make some things easier.
But I.
It might mean that people who don't have the background.
For.
Pre-trained translation works.
Sorry, I get
So, you actually have a big.
I remember that because I was there in the fourth generation.
We could just have. And you.
When-
So you know question.
Yeah, I think the answer is
Yes,
the device by for.
is Python.
Yeah,
So it's
right.
anyways, yes, right.
Yeah, those things what people make
Python is very, very slow.
generate.
It's like
What are the
So my own lecture is like a little software we are actually.
We have the.
Is not doing like we are basically adding up to like
intertwining the same building. That's just unprofessional.
like all the rest.
So there is.
The idea that now
we
you
need
do
to-
There's so much in the code
means that
already in Python. So like this is
No.
this we are as you correctly pointed out, we're adding more stuff. But in the grand scheme of things, we're adding like minuscule things. So and most of the checks will actually like be able to be speculated by
You want to talk about
the processor anyway, right? Because you're probably not going to fail your freeze check very often, right? That's the
You know, in Excel, recent version of Excel, you make it so
Yeah, so that's a good one. So really what we do, right, is that we so the time it takes to freeze something, that's sort of it's linear size.
Oh, you have
So there
something
is a
there.
clip set, but each of these are going to be frozen once. Right? And then we have cache header, the state, right? So that it's frozen in one check. Right? So basically
a few years
the
ago,
operation that
probably 5
you
years
do
ago now,
once is the
maybe
big
that's 5 years ago now.
and then the checking is super fast because it's just looking at the location that should be hot cache anyway. Yeah. But the memory cost is already there because so every object on Python has a object header. I mean, it's like most programming languages somehow, and we have basically just found the bits in that header that are confused, and that's the bit we are using to track immutability. So this thing is already counted. There's some extra memory costs. So
You got the data.
but like this is a super good question because like when we were discussing this, like so they're saying immediately like you cannot make the object larger, right? If you do that,
Things like Australia.
so like finding ways of doing this that are cost effective in terms of memory is super important. Otherwise, you couldn't do it.
And for the government, actually.
World economic policy.
This meeting is being recorded.
So, right now, the
Anyway.
because we have constantly no.
Thing.
Well, I mean, we're just hooking into the way, we're just hooking into the way Python manages memory normally, right? And I think actually in our scheme, you'll have less floating garbage, right? So floating garbage is basically objects that are dead, but the garbage collector has realized them are refrigerated, right? And so in Python, you will have floating garbage in terms of what cycles you create. But since we affect cycles immediately because we are reference counting, right, it's even better, right? And actually, if you think of how, like, is moving into Python. So Python today is where you have to change memory into regions, so you only check one region at a time. And that's like a way to make sure that the box check can stop the program, right? You want to stop the program, short check span as possible, right? Yeah. Right, but in our case, so freedom takes these regions and you collapse them into one, so you'll have like longer DC cases in the freedom column. In our case, we're almost getting to what's called only 5 garbage collection, where we basically collect garbage without stopping the program effort, because we're only based on this reference counting scheme. So we don't really need this cycle detection for our immediate. So we're actually making things faster.
Because I keep getting.
Yeah, well, I have that one, and it's actually even better, like the stuff that we want to do long term, where we are partitioning the memory into like lots of smaller regions. So because every region is isolated, they can be garbage collected individually. So rather than like dividing the entire chip into 3 chunks, we can have 3 million chunks. So they can have
it's basically, I do have to.
we can actually make things a lot better if we are just able to go in that direction.
On my manual.
Yeah, no, that's what we can do there.
Thank you.
Thank you.
The Java Options talk is on Friday, I think.
Yeah.
Good talk, sorry if I interrupted, but.
No, it was good. I think you broke the.
That was, I figured, I just, I'm sure I dived in, and I thought, oh, look, everybody's, sorry, it was quite warm up the top there. I should get some coffee and drink, and then when you, I don't know, it's good to see you, you made it.
Where should I start, that thing?
It doesn't matter where.
Do you want coffee? I can show you what coffee is. Yeah. Maybe there's even coffee out here, no? All right, let's do the morning, only coffee like
It's basically the Hungarian version of Gregory. So, and my middle name is Lajos, but I don't really go by Lajos. And yeah, and Lajos is equivalent to Louis. So I am Greg Louis. What's on that?
Actually, Louis. Okay.
Yeah. I hope that I will not run out of time, honestly. Yeah. Yeah, I mean, so running out of time on this one isn't that big of a deal because I'm also doing the next one. Yeah. But this is pretty information dense, and the next one is also pretty information dense. So yeah.
Are you ready?
As ready as I could be. Yeah. I don't know if you should wait for the others.
We can wait a bit.
They can be. We can wait like 2 minutes. And
Let's wait for the organizers maybe.
Yeah.
You get everything set up.
Yeah.
Okay, let's begin with the next session about like formal semantics and verification.
Yeah.
I think the second one as well.
Yes.
Gloria, can I tell us about mechanized group of connections?
Yes. That's it. Does this work? Yes. Okay. So let's start. So welcome everybody. My name is Gergely Turán, and I am a master's student at Eötvös Loránd University in Budapest, Hungary. And this talk will be about mechanisms of atomization in Erlang. And before I get too far into this, I want to say that these slides are very much so there is a lot of information here. So maybe it would be nice to only ask questions at the end of the slideshow. So before I get to the main part of this talk, I want to talk about formal semantics a bit, because I understand that this is mainly an Erlang-based audience, and some of you might not be that familiar with formal semantics. So formal semantics models the computational meaning of programs, and here is a situation that you might have run into during your work. Let's say you are given an expression in a programming language, and it could be in any programming language, not just Erlang. to evaluate. So you evaluate it and get back an answer. Then your colleague does the same thing, and they give a different answer. So what did you use to get these answers? Well, you both use your own favorite interpreters, compilers, or other tools that you might use. So logically, it would follow that that one of your favorite tools didn't really follow the language specifications to the T. However, it turns out that both of your guys' interpreters or compilers claim to follow the language specifications. So what happened here? So basically, the problem here is the language specifications themselves, but they are usually given in natural languages, such as English. And the problem with natural languages is that they are complicated and ambiguous, and that is not surprising because people are also complicated, and sometimes they could be ambiguous. But fortunately for us, there is another way to give specifications to programming languages, and that involves a language that is unambiguous, that is mathematics. And formal semantics is all about defining the meaning of programming languages using mathematics. And there is also another catch here, which is that mathematics might be unambiguous. However, people still make mistakes in mathematics. So everything that you will see in this talk was also formalized in the ROC proof assistant. And if you don't know ROC, it was actually called COC for a very long time. And this is an interactive theorem prover based on constructive logic. And so if you implement your formalizations into ROC, then you can make sure that when you prove theorems, you don't miss anything during the proof of these theorems. And so once we have a mathematical way that we defined our programming languages, that is great for us because we can do a couple of things like proving properties of programs and also deriving formal tools based on this specification. So getting this a bit closer to home, at our university for the last 5 years, there has been a project going on called the High Assurance Refactoring Project, or HAR. And this is about proving refactoring is correct. And the main language in focus is Erlang because of its interesting concurrency model. And the main contributor to this project is Peter Beretsky, who made formal semantics for the core Erlang language. And that was basically his PhD thesis. And so in this talk, you will get a bit of a taste of this core Erlang semantics. And then I will be talking about formalizing atom exhaustion in the semantics. And then I will be talking about a calculus called Galois that was developed. So Peter's semantics actually formalizes core Erlang instead of Erlang, and there are multiple reasons for that. So core Erlang is further down the Erlang compilation pipeline than Erlang. So there are many features in Erlang that are just basically synthetic sugar, and during this compilation they get desugared. So there are fewer things in core Erlang that need to be formalized. Another thing another reason to formalize core Erlang is because it's also in the pipeline for other languages in the Bean family, such as Elixir. So this formalization of core Erlang can also be used to reason about Elixir programs as well. And if you want to give formalization to core Erlang. Luckily for you, there is a specification available, and as you can see, it's really fresh and up to date. The last version of this file was made in 2004, so 21 years ago. So this file was used to formalize the language, and everywhere where it was not clear or it seemed out of date, the Erlang shell the Erlang shell basically decided what to do. So this is a short excerpt from the syntax of this semantics. So core Erlang expressions can either be values or exceptions other than values. And values are things like integers, atoms, and lists. And non-values are things like function calls or function applications. And core Erlang even has let expressions in it. So the semantics itself is defined in a small step style, and that means that we are doing reduction steps on semantic configurations. But that doesn't really mean anything until we define what a semantic configuration is, and it looks something like this. So in this configuration, you can find the frame stack and the regex. And the regex is the expression that we are evaluating, evaluating right now. And the frame stack can be thought of as the continuation for the evaluation. So the regex is just a core Erlang expression, and the frame stack is a stack of frames. And the frame is basically a core Erlang expression with a little hole inside it. And the idea here is that when we calculate the value of the regex, it will fit in that hole at the top frame. So the frame at the top of the stack. So this is what the semantic configuration is. And these configurations can be thought of as a snapshot during the evaluation. So this is one of the configurations during the evaluation of this expression: 1 + 2 + 3 + 4. And what is a reduction? So a reduction is basically an evaluation step, and it gets us from one configuration to a new configuration. And to give formal rules. So to give rules to formalize a programming language is basically the act of defining these reduction rules. And if we have these reduction rules defined, then we can evaluate some programs. So here are some reduction rules. So this is how a call expression should be evaluated. So the first step is, if we find call expression on the regex, and you can recall that the regex is the expression that we are evaluating right now, then what we need to do is we need to put it on top of the frame stack, and then start evaluating the expression of the module name. And once we've got a value for that module name, the next thing that we need to do is evaluate the expression for the function name. After we get the function name, we proceed to the first parameter of this function call. And the next rule looks a bit scary. It's not actually that scary. So if a parameter of a function was calculated, then we need to put it in and go on to the next parameter. And after we get to the end, what we need to do is call this eval auxiliary function. And what this does is basically so this formalizes the built-in functions in core Erlang. So, and here is an example evaluation for the ones here who are more visual learners. So we have a core Erlang expression
on the stack. Oh, and I should say that so this is the expression that we need to evaluate, and this is the initial configuration. So the expression is in the red X, and the frame stack is left empty. So we have this expression in the red X, and we just need to follow the rules. So the first rule was, if we have a call expression, we need to put it on top of the frame stack, and then this module expression needs to be evaluated. And luckily, that is pretty easy. The value of this expression Erlang is just Erlang. So we need to then put it in the little hole and go on with the function name. And the function name, similarly, the value of this is just plus. So we put it in the little hole and go on with the parameters. The first parameter is 1. It has a value of 1. So we put it in and move on to the next parameter. And this is a bit more interesting because again we have a function call here. So we need the first rule again, which was to put the call on top of the frame stack and then go along with the module name. And I think that you can guess what happens next. So continuing after a few steps, we get here. So we have 3 on the red X. The value of that is 3, and now we need the rest rule. So we have this eval of this call, and I said that this was just an auxiliary function. So this just needs to be calculated. So this is not even a reduction step. We calculate the function, 2 plus 3 is 5. And then we use the same rule again. And similarly, 1 plus 5 is 6. So yeah, and this is an end configuration because this configuration cannot be reduced any further. So, and another bit of notation, so this arrow with the star on top of it is a multi-step relation, is a multi-step reduction. So in multiple steps, we get from that configuration to this configuration. So and this, all of this that you've seen here is only this bottom layer of the semantics, the sequential layer, and the upper 2 layers are concerned with formalizing the Erlang actor model. But this paper doesn't talk about them, so I won't go into it here. I will need to go into this in my next talk. But just remember, this is just the bottom layer. So I need to talk about atom exhaustion a bit. So in Erlang systems and in Beam systems in general, atoms are stored in a so-called atom table. So every time we create a new atom, it will go into the atom table, and an important property of this atom table is that it has a fixed size, and it also never gets garbage collected. So after a while, the atom table will get filled up with atoms, and if we want to, my computer is about to die. Sorry, it's plugged in. I don't see all that. Thank you. So yeah. So where was I? So the size of the atom table is limited, and if we fill up this atom table, the default capacity of this atom table is 2 to the 20, so around 1 million atoms. But if we fill it up and we try to create another atom, then there is no more room to it. So what we get is a crash. So the Erlang crashes, and we will need to restart it manually. And the most common way that this problem would occur is during dynamic atom creation. So with functions like list to atom or binary to atom. And this is a function that is vulnerable to atom exhaustion. And in the real world,
this is probably not what you would see if we were talking about applications vulnerable to atomic exhaustion. But this is just a toy example to show us. So basically, if you input a number to this function, it creates that number of atoms. And as you can see, if the input number is big enough, then we indeed cause atom exhaustion. So how do we formalize? So how do we put in this atom exhaustion to a formalization? Well, the first thing that needs to be done is formalizing side effects. So if you remember this auxiliary function eval, it gives back the result of the built-in functions, but we can also give back a side effect along with these results. And the side effects are things like reading operations or writing operations, or what you care about here really is atom creation. And so every time, and this effect is an option because we might not get a side effect from a single from this evaluation, but we might get it. And so this is an example with list to atom. So previously, evaluating list to atom full would just give us the atom full, but with this new version, along with the atom full, we also get an atom creation side effect. So the next thing that needs to be done is to label our arrows. So if you remember this rule of function calls, we can we now need to rewrite it like this, and this line means that the thing about it is a precondition. So eval now has two arguments, a result and a potential side effect, and the result goes in the red X as before, but the side effect will be put on the arrow. And we also need to talk about the many-step relation again, which is formally called the reflexive transitive closure. And really, this is just an n-step relation and not a many-step relation. And an n-step relation can be two things. It can either be a zero step or a more than zero step. And if we do zero steps on a configuration, we just get the same configuration. And this is where reflexive comes from. And this is the transitive rule. So basically, if we get from the starting configuration and we do one step to an intermediate configuration, and then if we do n steps to get to this ending configuration, then what that really means is we did n plus 1 steps here. And so these rules need to be modified, because what we have done with the single steps is label them with potential side effects. And what we want to do with the multi-step relations is we want to give back the list of side effects that were generated along the way. So here is how the rules need to be rewritten. So if we do zero steps, then we didn't then we didn't do any side effects along the way. But in the transitive case, so we might have a side effect in the first step, and for the n step on top, this big L means a list of side effects, and on the bottom we will have a big L prime, and to calculate that big L prime is to do this. So basically, if during the first step we didn't have a side effect, then the list of the rest of the side effects will be given back. But if we did, then the side effect will be put into L prime, and also this L label needs to be put for
for the many separation as well. So formalizing atom exhaustion in this semantics could be done in two different ways. The first one is to actually formalize the atom table, and this would be more faithful to the Erlang language. The problem is we wanted to formalize atom exhaustion for the upper two layers of the semantics as well, but that would be pretty hard to implement if we did it this way. So this is the other way to do it, and so since we have this reflexive transitive closure with a list of side effects along the way, we can just trace the atom creations during the evaluation. And this two atom set helper function just transforms this list of side effects and gives us the set of atoms that was created along the way. And we also need to define two more things. One of them is the atom value set, or AVS, which is the set of already created atoms, and the other is the atom limit, or the maximum number of atoms that can be created. And if we have all of these, we can define what it means for a configuration to lead to atom exhaustion. But it means it means that two things need to happen. The configuration needs to lead to another configuration while generating this list of side effects L along the way. And the other thing is if you get the atom set, so if you get the set of atoms that was created along the way, and take away all the atoms that were already in the atom value set, so the atoms that were already created, the number of this set needs to be bigger than the atom limit minus the size of the atom value set, and this is notated like this. So, and it can be read as follows. So, given the atom value set AVS and the atom limit, this configuration KR will lead to atom exhaustion. And now we can also define what it means for a program to be vulnerable to atom exhaustion. And if you remember, the program evaluation always started with putting the program in the regex and having an empty configuration. So in this case, we are starting the program evaluation. So that is why the atom value set, which is a set of already created atoms, is empty. So for a program to be vulnerable to atom exhaustion means that given an empty AVS and an atom limit, this configuration will lead to atom exhaustion. So what if we need to prove that the program R is vulnerable to atom exhaustion? So we formalize the atom exhaustion. We need to prove this for a given R. But so this is just some notation that can be unfolded into this, and this is also just some notation that could be unfolded into this, which just looks frankly disgusting. However, there are a couple empty sets here, so maybe it would clear up, but not really. So what this bottom expression really means is the following. So there exists a configuration and a list of side effects, so that we get that configuration from R while producing those side effects, and the side effects exhaust the atom limit. And the thing is, this is very hard to prove in ROC, and specifically, because of this conjunction. So in rock, a conjunction needs to be proven one side at a time. But these two sides of this conjunction are very interdependent on each other. So we can either prove the left side first or the right side first. But going either way is not very feasible. So this cannot really be automated. So that is why the Galois calculus was developed. And Galois stands for generates at least n unique atoms. And the idea with this calculus was to not use these two atom set L, and actually to not use the side effects collected along the way in general, but to just prove that at least n atoms get generated when evaluating the program. And this is the notation for Galois, and it can be read as follows. So given AVS, the configuration KNR generates at least n unique atoms. So Galois has three rules to it. The first one states that any configuration will generate at least 0 number of atoms. And so that is an axiom, and it's pretty easy to see why. The next rule says so if we get from this configuration, this initial KNR configuration to K prime R prime in just one step, it is enough to prove to prove that this initial configuration KNR generates at least n unique atoms. It is enough to prove that this configuration generates at least n unique atoms. So what this rule says is we didn't generate a unique atom at the first step. And the last rule says it looks a bit complicated. It's actually not that complex. What this rule says is if during the first step there was an atom creation side effect, and the created atom AV has not already been generated yet, so it's not in the AVS, then to prove that we generate n+1 atoms during the calculation of this, you only really need to prove this, which is that we generate n atoms while evaluating from this configuration. So there were a lot of theorems proven about this calculus, and the formal proofs were done in rock, but the paper is a bit less formal about them, and I want to be even less formal. So the two theorems to remember here is soundness and completeness. So it was proven that if with Galois we can say that this configuration generates at least this number of atoms, then the configuration will lead to atom exhaustion. And completeness is the opposite. So if this configuration leads to atom exhaustion, then it will generate at least this number of atoms. And this is great for us because I mentioned that this atom exhaustion formalization cannot be proven automatically. However, the rules of Galois can be proven automatically. And so if we need to prove one of these atom exhaustion properties to a given program, we can just use this completeness theorem to convert this atom exhaustion this vulnerability to atom exhaustion into Galois. The Galois can be solved automatically with just one theorem in rock. So there is a, so here is a bit of an example evaluation. So this was the toy example of a program that is vulnerable to atom exhaustion. But this is in Erlang, and I said that the formal semantics is in core Erlang. So in core Erlang, it would look a bit like this. And this actually has a few meta variables in it, but you can just ignore them for now. And this figure is straight from the paper, because I didn't want to recreate it in PowerPoint. So the thing that needs to be proven here is the following. So we know that this program will be vulnerable to atom exhaustion, because for any atom limit that could be set for the size of the atom table, we can give a big enough n that we can exhaust the number of atoms. So for this example, the atom limit was set to be 2, and what that means is that if we generate at least 3 atoms, then the program will be vulnerable to atom exhaustion. And so this is a simplified derivation tree of this proof, and there are many notations in here, but the things to keep in mind is this at the bottom. So it says that program will generate at least 3 unique atoms during the evaluation, and for most of these steps we are not generating any atoms. So that non-generating rule needs to be applied. But when we are generating atoms, we always have this P on top of the frame stack, and I didn't put it here, but this P frame contains that leads to atom built-in function that actually does the atom creation side effect. So that is why when a step is done on this configuration, we generate an atom along the way, and we only need to prove that instead of generating just 3 atoms, we only need to prove that we generate 2 more atoms along the way, and then 1, and then we get to 0, and we know that that is an axiom because every program generates at least 0 atoms along the way. And here are some final thoughts for this. So this Galois calculus could be extended to the concurrent layer of the layers of the semantics as well. We have some ideas for that, and Galois is actually pretty general, and the ideas developed here could be used in the formalization of other vulnerabilities, and we can reason about them as well. And the final thought here is that formal verification works well alongside static analysis tools. So you might be wondering, so why are we proving that a program is vulnerable to atom exhaustion? Shouldn't it be better to prove that the program is not vulnerable to atom exhaustion? But formal verification and static analysis tools have the same goal in mind, which is to find vulnerabilities in programs. But static analysis tools can give false positives. But by the nature of formal verification, that cannot give back false positives. So these two tools can work very well in tandem together. So if a static analysis tool says that this program might be vulnerable to atom exhaustion, then we can check using formal verification that it is indeed vulnerable to this program. And before before I forget, I would like to thank Arseny Fomin for his work on this paper, because this was actually his master's thesis work, and he really should have been the one to give this talk, but unfortunately his travel couldn't be arranged because of visa issues. But I want to thank you all for listening, and I think we might still have a couple of minutes for questions if you have any.
We have time for one question.
Okay.
In your closing thoughts, you mentioned other vulnerabilities. Are these all related to resolve exhaustion, or do you have other vulnerabilities in mind?
But it would be great to ask Arseny about that because he really wanted me to. So he has many other ideas for this, but he was the main contributor on this paper, and I just came in at the last minute to help out. So yeah. Yeah.
Thanks for the talk. Just a general question. So I was wondering, is the Gamma language too incomplete? Because I'm wondering if you can, because basically, if understood, you need to execute the Redux inside the Gamma. So I was wondering about how impressive is the language, and if it will always eventually.
So we'll always eventually terminate. So the semantics itself. So the semantics rules themselves. So basically, there could exist an example where just executing the rules will. So basically, we can get infinite recursion here with these semantic rules, and so that is an interesting question, and I would need to go into a bit of ROC for this. So in the ROC theorem prover, infinite recursion is actually not possible, and that is because I mentioned that ROC uses constructive logic, and if we allowed constructive logic, if we allowed infinite recursion in constructive logic, that could lead to logical inconsistencies. So for the definitional language of ROC, which is called that is called Galena, by the way, you cannot have infinite recursion. However, in the tactic language of ROC, you could have infinite recursion. So if I thought about it, so basically, if we did have an infinitely recursive program, then that ROC tactic shouldn't ever. So we shouldn't ever get to the end of that ROC tactic, basically. Right. Should I move on to the next talk? Yeah. Or any other questions? No. See, don't see my reverse. Okay. So this talk will be about deriving an Erlang interpreter from the mechanized formal semantics of core Erlang, and so this talk so this paper is also one of the latest papers from this high assurance refactoring project, and I've mentioned with formal semantics that if you have a formal definition for a programming language, you can build formally verified tools on it, or you can prove properties of programs. And the last talk was about proving properties of programs, but this talk will be more about deriving formal tools from the semantics. And the main topic here is a formally based interpreter. So deriving that from the semantics itself. So I've mentioned before that the semantics formalizes core Erlang because it has fewer language constructs than Erlang, and because it's also an intermediate language for other languages in the Bean family, like Elixir. And I've also talked about the syntax in my last talk, but so repeating it a bit. So a core Erlang expression can either be a value or a non-value. Values are things like integers, atoms, or lists, and non-values are expressions like function calls or function applications. So in the last talk, I only really got into the sequential layer of the semantics. However, there are these two upper layers here, and these are the layers that formalize the Erlang actor model. So, but a bit of we should look back in the sequential layer again. So as a reminder, in the sequential layer, reductions are made on these configurations. So we have a frame stack and the regex, and the regex is the thing we are evaluating right now, and the frame stack is the continuation for the evaluation. And I brought you some more reduction rules from this layer, and these are how to evaluate the try expression. So if we have a try expression in the regex, what we need to do first is put it on top of the frame stack, and then evaluate the expression in the head of the try expression. And that expression can either evaluate to a sequence of values or an exception. And this is a sequence of values because of multiple bindings here. But if this expression evaluates to a sequence of values, what we need to do is go on with the E2 branch because we didn't have any exceptions, and these values that were calculated will so these bindings here. So these are the values for the bindings here, and these values will need to be substituted into that expression, and through this substitution operation. So basically, these variables will get syntactically replaced by these values. And what happens if that expression gets evaluated to an exception is we need to go to the catch side, and in the catch side there is also some substitutions going on because Erlang expressions have Erlang exceptions have 3 components to them, and these components need to be substituted in to these bindings. And the last rule here, with the exceptions, is how to propagate an exception. So I've mentioned that the frame stack is the continuation for the evaluation. And what happens if we don't have a try block on top of the frame stack? Well, we need to propagate that this exception until we either catch the exception in a try block, or we run out of the frame stack and terminate the program. And give back the exception at the end of the evaluation. So this was the sequential layer, and I want to talk about the Erlang actor model a bit as a refresher. So in the Erlang actor model, processes are called actors, and they communicate through passing messages, and these messages arrive at the mailbox of the other of the process that it was sent to, and that other process can deal with these messages when it wants to and how it wants to. And processes can also spawn other processes, and also processes can be linked together. And what a link means is that when one of these processes terminates, all of its links will be informed of this termination, and they can deal with this exit signal that was sent out in the appropriate way that needs to be done. So the Erlang actor model can be formalized using two layers. And so the middle layer that builds on top of this sequential layer is called the process local layer. And this layer will do reductions on processes. And the upper layer will be called the inter-process layer. And that will do the orchestration of everything. So all the processes inside the Erlang node. But for the process local layer, I said that we will be doing reductions on processes. And processes can either be living or dead. And the living process is basically a frame stack, or LX, that we have already seen before. And they also have a mailbox and a set of linked PIDs, and also this trap exit flag. And processes can also be dead. So after they terminated, these are notated with T, and T is just a map between the linked PIDs and the exit signals to be sent out. And in this layer, reductions are made during actions. And the actions can be a few different things. So an action can be tau, which is a silent reduction step. You will see in a moment what that means. And actions can be send or arrive, and these control the signal sending and signal arrival. An action can also be spawned, and this is what does process spawning. And it can also be self, and self just gives back the PID of the process. And by the way, on these slides, everywhere you see an iota is a process identifier, so a PID. And here is so here is an example of a reduction in this process local layer. So we have a process here, and this needs to be reduced using this action. So this is basically sending out an exit signal, but from a living process. So by manually calling Erlang exit. So as you can see, this frame is on the frame stack. The value to be sent out with this exit signal is V, and if we do this sending action, then this is what needs to be done to this process. And remember that this process local layer is only concerned with this process itself. So the other process that will receive this exit signal, well, that will come along later in the final layer of the semantics. But sending this exit signal. So what sending this exit signal means to this process is just that the top frame should be taken off the frame stack, and we need to give the value true as the value as the LX. And this is another reduction in this process local layer. So you might have been wondering what a tau action was. And the tau action is basically the action that connects this process local layer with the bottom sequential layer. So to do a tau action on a process just means that we need to do one of these sequential, one of these reductions in the sequential layer. So getting from one configuration to the other, and so in the process local layer, you can see the new frame stack and the redx here. So this so unlike the sequential layer, which is deterministic, this process local layer is actually non-deterministic, and that is for a couple of reasons. One of them is arrival actions. So at any point in time, a signal might arrive to a process, but actually, if we don't count arrival actions, then a living process will know how to go on with the evaluation. So that would be deterministic. But since arrivals can happen anytime, this makes reductions on living processes non-deterministic. And actually, reductions on dead processes are also non-deterministic. So a dead process can only do one thing, and it's sending out exit signals to all of its links. And we know that there should be an order for this, but this order is actually never specified anywhere. So that is why this is another point of non-determinism. So that process can send out exit signals whichever order it wants to. And the final layer is the interprocess layer, and this does reductions on node configurations, and these node configurations are a bit different than nodes in Erlang, because so we have a process pool, which is a map between process identifiers and the processes that are identified by them. But a node configuration also has an ether, and that is where signals and that is where signals float around after they've been sent out, but before they've arrived to their destination. And this ether needed to be formalized because of this signal ordering guarantee. There is actually only one thing that we need that we know about signal orders, and is that sending a signal between a source and the destination, or actually I should say that sending multiple signals between the source and the destination, so the order of those signals, so the order those signals will arrive will be the same order that they have been sent out. But otherwise, the order of signals arriving is actually also non-deterministic. And so I said that you can think of this interprocess layer as a layer that orchestrates that orchestrates all of these reductions. So here you can see one of these reduction rules, and all of these will be pretty similar. So what you have on top is a reduction in the layer below. So that is actually in the process local layer. And what this reduction says is if we did a reduction on a process in the process local layer and the action was a sending action, here is what we need to do in terms of the whole system. So you had the ether before. That signal that was sent out needs to be put in the ether. And as for the process pool, the process associated with IOTS, it used to be P, but we made a reduction on it. So now the process associated with IOTS is now P prime. And as you can see, for this bottom part, the interprocess layer, for alongside the action, we also need to give the PID of the process that the action was done on. And this is another rule for the interprocess layer, and this one is much simpler. So here is what the tau action means in terms of the whole system. So if we do a local step on the process, then the ether is unmodified. But the process pool is modified. Before we had this process P, but now iota is paired with this process P prime. So this interprocess layer is also non-deterministic, and it's not just non-deterministic because of the process local layer below it. It's also non-deterministic because every reduction step we need to choose which process to do the reductions on. So as I mentioned before, everything you see here was also implemented in the rock proof assistant, formerly known as COC, so these three layers of the semantics were defined using inductive definitions. And for this paper, what we wanted to achieve was deriving an interpreter from these rules. And actually, so deriving this interpreter is actually pretty straightforward, but there are a few steps that need to be taken along the way. So these inductive definitions are not inherently executable in ROC. So the first thing that needed to be done was to make three functions that work equivalently to these inductive definitions, and so these functions would need to be computable, and this way you can do these reductions automatically. And as you can see, so these functions need to be equivalent, and that equivalence actually needs to be proven. So as for the sequential step function, if you remember, there were 4 rules for those trie expressions, and here they are actually in the code. And yeah, the formalization it's kind of unreadable here, but what you need to focus on, basically to minimize the number of branchings here in ROC, we match on the regex first, and then if we need to, we match on the frame stack. And if we need to match on anything else, then we match on those after. And but you can see here with, for example, S-trie, that all this rule needs is a trie expression to be in the regex. So that is why we are not matching on K here. But for the others, we do need to match on K. The process local step function was a bit interesting to define, but one thing that I want to point out is the arrival of exit signals, and these are the rules in the semantics, and as you can see, there are a lot of preconditions for them. So to make this into a function, a lot of nested pattern matches were needed. And figuring out a good order for that was a bit of a challenge. And as for the interprocess step function, so in this function, the first thing to match on is this pool lookup, and that is equivalent to this. And this is because for this function, a node needs to be given along with an action and the PID of the process that we want to do that action on. And we need to look up the PID in the process pool, because we need to actually see if that process is in the process pool. But otherwise, when we do that, we can just proceed with the actions accordingly. So that's great. Now we have a function that works equivalently to the interprocess layer, and we can do steps using it. However, for an interpreter, it is actually it is actually not very convenient to use this. And that is because this action parameter needs to be provided every time. And it's not really an interpreter's job to construct these actions every time. So we decided to make this interfacing function that we call the node simple step function. And for this function, we need to give a node, and whereas for the previous function, we needed a PID and an action. This function needs either a PID or a pair of PIDs. So I've mentioned that with living processes, the actions other than arrival are deterministic. So if we give this function a PID, then we do a non-arrival action on that process associated with the PID. But if we give this function a pair of PIDs, then if there is a signal floating in the ether between these two PIDs, then the function will make that signal arrive to the destination. And so the interpreter itself cannot be completely constructed in ROC, and that is because, as I mentioned at the end of the previous talk, you cannot have infinite recursion in ROC, because it would lead to logical inconsistencies. But there is a way in ROC to extract these definitions into other languages, like Haskell, OCaml, and Scheme. And for this project, we chose Haskell. So we need to extract this node simple step function into Haskell, and for that, and actually is using the default extraction works great, but during the extraction process, a number of optimizations can be done on the way, and that is because ROC gives us ROC gives us some optimization options. So these are things like replacing ROC data types with Haskell data types, or ROC functions with Haskell functions, and also we can inline functions. And the three major optimizations that we pointed out in the paper were as follows: making substitution strict. So if you remember those try rules, so when variable bindings were calculated, so after variable bindings get calculated, they need to be replaced in the program. Yeah. So the variables need to be substituted. That's not how I should say it. So the calculated value needs to be put in to the place of the variable that was calculated. And to do that in the semantics, we just go through the whole structure of the program, and and replace all these variables when they need to be done. However, since Haskell evaluates expressions lazily, this didn't really happen, and there was a pretty nasty space leak issue with this. So that is why these substitution functions need to be made strict. The other optimization here is replacing the extracted map and set operations with the Haskell variants, because they were just more efficient. And the last thing to talk about here is simplified substitutions. So the substitutions were defined very generally, and a lot of meta theory was developed along the way. However, for this specific use case for Erlang, substitutions can be simplified a bit. So that was the third optimization step. So after we've extracted this function and optimized along this extraction, we also need a scheduler component, and that is because so now we can do reduction steps on a node, but we still need to pick which process to do these reduction steps on, and that is the scheduler's job. The scheduler picks one of the processes from the process pool to do these reductions on. And one other thing that was defined is what we've called the interpretation cycles, and that goes something like this. So when the scheduler chooses a process to be in focus, that process in focus makes at most k non-reliable steps, and then if the process terminates so if a process terminates during this k non-arrival steps, then all of its links will get notified immediately. And the third thing in this cycle is all signals floating in ether will get delivered. But otherwise, the scheduler is free to choose which process to make the non-arrival steps on. And actually, just defining just defining this scheduler and the interpretation cycles. So just by defining these two things, we eliminate all points of non-determinism in the system. So every time we run this interpreter, we can get the same result. So yeah, and the last thing needed here is for a way to integrate all of this into the Erlang ecosystem, and for that we needed a so-called pretty printing component, because the semantics is for core Erlang after all. So we piggyback on the Erlang compilers compilation between Erlang and core Erlang, because that is actually pretty well founded. So we convert our Erlang code into the abstract syntax tree in Coq, and then we extract that definition of the program in Rock. And now we can use the program in the interpreter. And so another tool that was built in this paper was a so-called computation graph explorer, and the idea came from this figure, which was in one of the previous papers in the project. And so basically, as I said, there is a lot of non-determinism involved during the evaluation of these node configurations, and what this figure shows is this program called PMap, which is basically a parallel execution of maps. It just splits a list in two, and then does a map operation on both halves of the list, and then concatenates them together. But doing this concurrently leads to many different interleavings that are possible. And this figure was made manually by hand. However, since we now have a way to do these reduction steps automatically, we can make a component that makes figures like this. And actually, so this is basically the same figure as this one, just some nodes are more compressed here. And here, every one of these nodes is one of those node configurations. So with the process pool and the ether. And you can see that many different execution paths could be taken. And you can also see that, that this is not a tree, it's a proper directed graph. So some paths can lead to the same node configurations. And as I said, this figure can now be built automatically. So for closing, here are some pros and cons for deriving an Erlang interpreter from formal semantics. One of the pros is the interpreter can be made with little effort. So as you saw, there were many steps involved, but they were actually pretty straightforward. And the interpreter is formal based, which cannot be said of most tools made these days. And it can also serve as a reference interpreter for other interpreters and compilers. And reference is a keyword here, because as you might imagine, building an interpreter like this will not lead to very efficient calculations. And that is because of two things. One of them is that reduction steps are high level, which are inherently slower. So, I mean, compiling into Beam code and then just running that would be way faster because it is just lower level. But the other thing here is that that inefficiencies in the formalization can carry over to the interpreter as well. And to illustrate that, this is an insert so this is an insert from a performance data table in the paper, and this example is a concurrent program with 100 processes running, and the four rows are the four correspond to the optimization steps made during the extraction in ROC. And I don't really want to bore you with the details, but the thing here is even at our best version of this interpreter, where substitutions are made strict and map and sub operations are replaced, and we use the improved substitutions, up to 96% of the time is spent just substituting variables, because we need to go through the entire structure of the program. So a solution to that would be to redefine the semantics using variable environments instead of substitutions. And I would like to thank all of you for listening to me. And I would also like to thank Peter Beresky for his work on the semantics, and Arden Fomin for that graph, that computation graph exploring tool. And also I'd like to thank EEF for their financial support in this paper, and finally the organizers of this workshop for enabling me to travel here to Singapore and present these two papers. That's about it. And I don't know if we have time for a question. I guess probably not.
No, I don't think, like maybe while Max gets.
Yeah, sure.
You can take one.
So.
Thank you for the interesting talk. During the reduction rules into something you could execute by doing a proof. Well, this reduction rule is the same as this function. Instead of that, have you considered just proving interesting theorems about the reduction rule, which give you something that can execute? So for instance, if for something simple like lambda calculus, you can take the reduction rules, prove preservation and progress, and then from that you immediately get something that you can execute.
Well, I think that would definitely be an interesting thing to explore in the future. So proving proving some theorems and like making those executable. Because the thing is with the current state of this interpreter, I know that I state that it's just a reference interpreter, but it's still a bit disappointing that is really quite inefficient. For that, I think that many things need to be explored too.
Okay, we have to talk to you about that offline later. I'm Bill Lockwood from Edinburgh.
Yes.
That would be before giving the talk. I tried. I tried. Yeah. There we go. I used to I've been working with them for a while. It's so nice. Well, Nick left. Yeah. Yeah, it's no shame. I was looking forward to it, but he left right before I joined. Because I approached him. Now I understand why in this transfer I actually took a reviewer of my last right on time. Sorry, I'm not sure the problem, but for me, these are no problems. Write down on it. Yeah, I fully believe that.
You can go to Mustafa.
Yeah. Actually, we are also. It's probably if I practice, I'm almost done with it. I've been working with the capacity recommended for a year. You guys like going for working on it.
Yeah, but I mean,
Yes.
like for.
Oh my gosh. I'm probably
Yeah, unfortunately, you can't get there.
Oh, now you know Miss Extra. So it was a year ago, I was at ICFP. Yeah. I know. But I don't. That's some. Sorry. And above all, the results. You know, I mean, to be honest, I think that's pretty good. And you're using semantic types, right? Doesn't that make everything easier? Huh? Doesn't that make everything easier? Other than performance?
Performance-wise works very well. I mean, it's we type checked that the remote campaign, which is 25,000 modules, more than 1 million lines, takes 17 seconds.
Oh my god, 1 million lines is nothing for us.
Yeah, I know. For you.
Yeah.
70 seconds.
70 seconds. But when we hired Victor, I was hoping we could get semantic subtypes because people expect these things to be complete. And the syntactic ones are not, and so I was really hoping that we could do things your way.
So explain me why what's the problem of adding of using semantic subtyping? Apart from when you try to do reconstruction, is that's the problem?
Yeah.
I mean,
it might be maybe. So I talked to Victor about it, and it's obviously a lot of work to rewrite the type checker, and it's hard to justify big projects. But I think he also said that
But
performance
you said you wanted
was
to be
concerned.
semantically sound.
No. I said I'm not going to define soundness. So our goal when we were working on it was syntactic soundness. Yeah.
Sorry, I don't even know what you mean by that.
By syntactic soundness, I mean progress and preservation.
Okay, but then you need to give all the detail. But the point is, if you want anything.
It's a lightning talk, it's 15 minutes.
If you want anything with any kind of theoretical properties such as that, then you need something that comes from a good theoretical basis. And the appropriate theoretical basis for what you're doing, I would think, is semantic subtyping.
I don't disagree.
Sorry?
I don't disagree with you.
When you say appropriate, there are plenty of syntactically sound, so
Yeah.
there are plenty of good type systems with union types that just do normal progress and preservation.
But
So
you also said you wanted to capture the way people were using it in practice.
that's right.
And I expect that what people are doing in practice is semantic subtyping. So if you don't support semantic subtyping, then you're going to get exactly the mess you described, which is here's something everybody writes, I don't know what to do with it.
Of course.
Yeah,
Of course.
so the only point is if you
So
use
the
semantic
point is, you're saying we're resource limited.
Of course.
What I'm telling you is my advice to you. First, you can ignore my advice. Of course, I'm not working in the context you're working in, but I have spoken with, I came to this specifically because I'm interested in how people do this stuff in practice, right? You've got all these people at Meta who have done this in practice. I expect if you talk to them, they will probably tell you what Bethany and I are telling you, which is the good match for what you're doing is semantic subtyping. And therefore, if you want to achieve this, you'll have to put that amount of work into it.
I completely agree. Yeah.
So you need to go back
so-
to your bosses and say, either we can do nothing or we can do it with these
Well,
resources.
we don't have nothing actually, so I think we have a pretty good code base with what we have now. People are quite happy with it, so I wouldn't call it nothing.
And your evidence that people are happy with it is?
Developer surveys.
Yeah.
And
So let's say that they type check just one program.
so
Which
internally
may
to the company-
simplify things, no?
Yes, so it's internal to the company, it's one big mono repo, and we're allowed to change the code base at the same time that we're changing the type checker. So over time, one of the things that Victor has done is work in the code base and massage it to be more amenable to type checking.
Yeah.
So I'm not disagreeing with you,
So this particular problem you mentioned.
it's gone. So they rewrote the code.
So why are we talking about this problem? Since it's not a problem anymore.
If not only
Why are we talking about when you write an interpreter, you interpret the program? That was one of the other talks. Anyway, I thought it was an interesting problem. I wanted to learn something, have a fun discussion. I would like to say, how interesting is it that what is the type of the empty list? Oh, it's the type of top, like a list of top. That's insane, and that's the one that won.
So you want my answer? The type of the empty list is the empty list. Yeah. But you need singleton types.
Well, listed none is the type of the empty list.
No, I disagree, sorry.
Oh, why not?
Because this is not an interesting discussion, so I think it's kind of a fucked up thing to say why that talk, but go ahead.
So because none is the empty type. Okay,
Yes.
and you consider a list as a associative products. Okay, so if you make a product of the empty type with anything, it is the empty type itself. So the list of none is none. Therefore, you can subsume it to anything.
With the list of none is none.
Yeah, list of
So
none is a
I can return list of none from a function that says it returns integer.
You cannot return a list of none because actually if you return a list of none, it's like returning none. It means that your functions must diverge on every argument.
So if I have a function.
So you're, in your definition, you're making an approximation somewhere, right? Because in practice, how many things are there type listed?
So-
There's one, the empty list.
No, none.
He's saying there's
So
zero.
maybe we are speaking of different none. For me, none is the empty type. Okay.
No,
which
for
is-
me, none is the empty type. That's what I meant.
Same.
List
Okay.
of none.
List
List of none is list of things where you can't have any elements.
exactly. So it's the empty list for me.
Correct. So
But
list of
it is
none.
not list of none because list of none, it means it is a list that contains a value that doesn't exist. So it is the empty type too.
No, it's a list of any length. All of its values must not exist. There's only one possible length, which is 0.
No, Because.
So you're a Platonist, I'm a formalist, he has a different formal system than you, it does work out.
Yeah, but I'm just trying to figure out what formal system he even has.
It does actually work out.
Just list, it is our product, okay? And our product.
No, there's a sum in there, right? Because they can have arbitrary length.
Okay, associative product nested on the right.
Yeah, but if I take the product of empty list, if I take the product of one, sorry, if I take the sum of one, let's have that list of A. What is that equivalent to? It should be one or A squared or A cubed.
No, it's
or
not part.
so on.
No, it's not the union because this is an infinite union. It
Yes.
doesn't exist an infinite union in my system on list.
Right. So you're talking about your system. So in my system, I'm perfectly happy with infinite unions because I'm talking about the meanings of things.
Yeah.
You're doing an approximation to that, which is fine. Just tell me which approximation you're using.
I just told you. For me,
No, it's obvious to you, but I'm stupid. Explain it to me.
Okay, so a list of integer is integer equal list of integer product. Sorry, list of integer equal integer product list of integers, or the zero tuple or empty list.
Right. So in that case, since there's an or there,
yeah,
then the list of none should be the empty list.
Yeah.
But it's the empty list because it's empty. It's not the empty.
No, the empty list is an element. It's a value. Okay,
Right.
But it's not a value of the list of empty elements. That things doesn't exist. It is the empty
list of A is equal to A times list of A or
empty list.
Yeah. So by that definition, list of none should be equal to empty list.
No.
Why not?
Because
you just hold on. Let me just check. I understood what you said.
Okay.
List of A is equal to A times list of A or empty list.
Yeah.
I'm going to pronounce empty list Y. Is that okay?
Yeah.
Okay. So no, pronounce empty list or empty list. So if you put 0 in there for A, it simplifies to empty list, not to 0. The product simplifies to 0,
Okay.
but 0 or empty list then simplifies to empty list.
yeah, but in that case, you have just the empty list.
Yeah. But,
okay.
But
it is not the type of all the is not the list of empty. It's the empty list.
All I said was list of none.
Maybe you should pronounce it
definition
one.
is
Just pronounce it one.
list of none is equal to
It's a symbol. You but if you
the
try,
empty list.
I mean, if you try how can I say? It is a matter of syntax.
In your system, am I allowed to write open bracket and then 0 or none or whatever stands for the empty type? And would that simplify to?
No, what you have, if this is the constructor is list, okay, what you can do is just to have the empty list without anything inside. It's the
List
different.
of, and then what do I write after inside the brackets?
Nothing. No, not list.
So I can
Okay.
speak his language.
Okay.
Okay.
It's not my language.
You speak it.
I don't like it. We speak the same language. No. See, got it.
Sorry?
No is a word of the type.
Yeah. Okay.
Anyway, sorry. So for him, I believe what I call lists is actually a union of two things. The list that can have things in them, like a list of strings, a list of integers, and so on. And this other thing, I think you said at one point you wanted to pronounce it one.
Okay, he's restricting lists to non-empty lists. When he says list, he means non-empty lists.
It means non-empty lists and
Union.
union,
Empty list.
this magical thing that I'm gonna call one, because for him, empty list is not a list of empty, which is it makes me sound insane when I say it, so we'll call it one. It's a unit of non-empty lists and one.
Yeah.
And for him,
So
the
the
zero
non-empty list
thing
of zeros
is an
before zero,
impossible value,
yes.
and if something contains the impossible value, it's also
Right. You
impossible.
said list when you meant
But you would also
non-empty.
say that the third item of a pair is also this empty thing.
Yeah.
Which is this insane value where if you have one, you have a proof of everything.
Yeah, but and actually, if you think that in Elixir you can do it because you can use a different terminator for list, which is not the empty list. So you can consider it the terminates not by the empty list, but just by 32.
Improper lists.
Yeah, exactly.
Erlang has that as
Yeah.
well. Yes.
It's an improper list.
Doesn't Scheme call that just end of list for the proper end of list value? And then you can also end an improper list with any other value that's not the special end of list value.
Sounds about right to me. So we make choices, right? So most of the code that people wrote at WhatsApp, when you were saying your thing is valueless if you didn't do it this way, come on. We had very little bad code, and we only massaged it a little bit, and the whole thing type checks now. So it is an approach. I'm pretty happy with it. And one of the things that we got away with was saying if you have an improper list, that's bad, don't use improper lists, because we had maybe 3 of them and they're all mistakes. So just like get rid of them. Like they just forgot the syntax of Erlang and wrote something stupid. So also we couldn't change the syntax for the language of types for Erlang. And I don't think it's very good at expressing that. So
Yeah.
you have to use maybe improper list, which means maybe it's an okay list, maybe it's not. Fuck that, we just didn't deal with it.
But I'm guessing so from Erlang or OTP, we cannot do those changes because of historical reasons. And otherwise we will need to rewrite the whole thing. And no one has time to fix that. So that's why we still need to live with.
If we were able to move a code base that's so large, I'm not allowed to tell you how large it is because I'm under NDA.
Okay.
Most Erlang code bases are not that big. And if you have a dynamic type, you can say gradually convert. So what we did was we moved one file at a time. So you write typing equalizer at the top, you make your file good. Everything that calls it is also good. You have teams that own their little parts of the code base. They're incentivized to make it good because they get good ID support and errors. And you can gradually adopt a better typing machine.
But if it's through your team, is the whole size of the Erlang OTP team. Or
Sorry,
bigger.
we just wrote a type checker.
Yeah.
We wrote a type checker for other people that own their application. And we said, if you type it well, you get all these benefits. And they said, ooh, we want to type it well. And then they typed it well. It's completely possible.
Yeah, but there's not going to fly.
You say that.
Because I
However,
tried, because
how happy are people with dialyzer? I'm just saying, like, if you go whole hog, accept any fucking
But
bullshit out there.
that's
you get
what
things
we are
that
trying.
we're betting on
That's what we are trying.
types.
That's what we are trying to do.
Yeah, and yeah, so
Excuse
when
me,
you said
I'm not-
we didn't do anything of value if we didn't do set theoretic types, show me.
I never said.
Oh, okay.
No,
Show
I'm
me,
not trying
yeah.
to say that what you do is wonderful. I mean, you have constraints that we don't have, so that's
Yeah.
incredible.
But also, I think
But
we have no evidence that set theoretic types can work for a real programming language. If you get this into Elixir, and you succeed, we go to Meta and we say
it is in the
look,
last pre-release. Right.
okay, if it can work at a code base our size, if we prove it out, if it's good with our code base,
So if you know,
then I will go to Meta and I will say, why are you allowing the code at Meta to be worse than the code in Elixir? We need to adopt this
it's
thing.
if you know Jose, you know that it doesn't do any modification that cannot be satisfied by the whole community. I mean, it's not satisfactory for the whole community. We are doing it little by little. For example, we don't have polymorphism because it's too slow, etc. But
It's a choice between polymorphism and
I know what you're gonna say.
Big polymorphism.
Yeah, so we actually have some really highly polymorphic code. It's kind of interesting, like to represent, we have like a parameterized XML type with these nested recursive data structures with arbitrary stuff in them. That was the most challenging thing to type check. I've given talks about that, and I think it would have gone over easier.
But in any case, these things, but what we do is that we solve it with multiple intersection. Because it's a result that intersection types are more expressive than ML, but it's not compositional, of course. That's the problem. But if you have essentially you look at every place where you need to use the polymorphic instantiation, and then you take the intersection of all the possible instantiation to the areas. And that's the problem is that then there is a little bit of explosion. So for example, they release they have now the 19 release candidate 2 because of when you do pattern matching and you give as a result a function, you have big unions of arrows, and this may make the subtyping explode. But we use actually it seems that it works because you use so we represent types as binary BDD, binary decision diagrams, and you keep the union lazy, and apparently everything works. But
so this kind of stuff, is it fair to say it's in the like CDUS tradition, like that kind of?
Yes, but it is redundant. There is a lot of work to work with Elixir because you have to do a very precise analysis of the guards. Okay.
Yep.
In CDUS, you have patterns, and every the set of values that are accepted by a pattern is a type. With guards, this is no longer true because all the list of Lang 3, okay, there is not a type that captures exactly.
Oh, but you can't write a guard that says that.
Exactly, but you cannot write a type that characterizes exactly the values of that are captured by that guard. So you have to do a fine-grained analysis with a number approximation and a number approximation.
So one thing that we ended up having to do that sounds familiar in that kind of area, and Ilya worked on this, and it's the most difficult code I've ever reviewed. I wanted to see if you handle this stuff. You probably do. So when people basically represent algebraic data types as a union of tagged tuples, where the first item of the tuple is an atom that says which branch to go down, they're basically doing this so that they can write 4 functions in one and dispatch on the first atom. You definitely support that stuff. Hell yes. Good.
Yeah, that's
good. That to me is the way to write good Erlang.
Yeah, that's easy. I mean, for that you need singleton types.
Yeah, of course, for atoms.
Yeah, exactly. So actually we could do.
But you also need to remember paths for nested atoms. Or sorry, for nested tuples that are distinguished by the atom in the first slot. You need to remember the path as you're refining, right?
Yeah, okay. You mean do what is called narrowing?
Yes. Narrowing, occurrence typing, flow typing.
Yeah, that's actually there is a paper on that in which we presented the principles. So it was in programming languages last year, and also we have just submitted a technical paper with all the guard analysis that allows you to precisely track. But we do really smart things. That is to say, for example, if you have some guards which are separated by OR, then we split it, and to infer the type of the function, we take the different OR and we do an intersection. So we do exactly say what will be the result according to the guard that was.
Just for the history, so you know that I didn't ignore all your work and then write this. It was 2020. It was during COVID. None of this work was out yet. And we saw Victor Landon, your student's dissertation, and said, hire this guy. And then I left the team. No, not for that reason. I really like Victor.
Me too.
Yeah. But that's because, and now we have.
He promised me that it would make an Oculus with discount.
Nice. So I didn't have the benefit of building on the stuff, but even if I did, we don't know. Like, please figure out polymorphism. Yeah, we really like
and the polymorphism. So I talked to Victor, and Meta is coming to meet us in November, and he said that the most important reason is how to report errors. It's really difficult to report.
That's black magic. Reporting errors.
And that's why he said that's why I don't know if really secure the types can work.
For polymorphic.
I thought I liked structural types until I started working on trying to make the error messages good for them. And then I was like, what the fuck? Like, people don't like the wall. We actually had some cool strategies. We show the mental model I'm trying to get is that you show stack traces, kind of like the runtime. And so you're like, this is basically what we tried to do as the type checker. Scala used to have a debugger for this stuff. I actually think it would be great to drop a debugger in and then have people figure out where their giant union came from.
You can look at the error message of Elixir. That's pretty interesting. What we did in Seduce is that when we do subtyping, we also built a witness, which is for us, subtyping is checking whether a type is empty. Okay. Because S is smaller than T, if and only if S intersection of T is empty. Okay, so we try to build a witness while we do the subtyping that inhabits that type. Okay, and if we succeed, then we have the witness to show to the programmer, say, you see, this value gives you an error, and then there is some black magic to just removing away all the context that is not interesting, just to give the part of the value that show to the programmer why there is an error.
So for us, we didn't have, when I was working on it, an ability to say the intersection of the stuff is empty. We only had the intersection of the stuff might be empty because we couldn't look inside everything. Because of opaques.
Yeah, opaques are like private types.
Completely different question. You mentioned gradual text. Which form of gradual text are you using?
Huh.
The one by Victor.
So when I was so we used something very ad hoc. I didn't work on it. My teammate did the ad hoc thing, got the job done, and then Victor came and made it better. And I don't think I could talk so sensibly about what Victor did after I left, but it was better.
Is there anything published on it?
Unfortunately, I don't think so. You would know, right? You're still in touch
For
with Victor?
well, there is the Victor thesis, and we have there is a paper with the Jeremy Sick, myself and Victor in Populo 20.
Oh, I know that paper.
Yeah,
I love that paper. That's my favorite paper.
Oh. I mean, I didn't pay this guy. That's so wonderful.
Yeah, so I left the Erlang world and haven't kept up with how much it's improved since I left.
And so actually the Victor thesis is even much better because there are things that are incredible in the sense that you can represent every dynamic type, any type with dynamic inside, with a couple of types, with two types that are no dynamic. So you can consider the smallest type that you can obtain by replacing dynamic with a type, and the largest type. Okay, you take these two types, and this represent in this way you can represent all of the dynamic types, and you can do all the subtyping, precision, and consistency, just working modeling these two types. And yeah, sincerely. And actually, this is exactly the way it is currently implemented in Elixir. Usually, what we have it's a descriptor. So for us, types are a descriptor record where there is one field for each type constructor. So the one for arrows, the one for products, for maps, etc. And there is an extra one that for the dynamic one, which points to another descriptor, which is the upper one. And the things you do, you work really modularly. You have to, if you have the lowest and the highest, this invariance is preserved, and just it's working with the gradual typing, just the double of work. You work with two types instead of just one. And that's really incredible.
Yeah, so for this, we called it dynamic.
So you use that, I guess, because with Victor.
So one of the first things that I did notice that Victor added was when you're returning something from a function, before, when people couldn't type the thing, they would say, oh, this is dynamic. And then Victor added is the upper part dynamic, or is the lower part dynamic?
Exactly.
And oh fuck, it's so much better. Like better error messages. And you don't have to say game over. You can say game partially over.
But the nice things is that you define that subtyping and precision are just with that. So subtyping is if you have two dynamic types, the lower is smaller than the lower and the larger is smaller than the larger, while precision is the lower of the lower. So it's a shift of the two. The other is one containing the other.
So Nick Benton didn't like this.
Okay.
And the
it's better than the left, but he's gone.
Yeah. Well, I could say
That's
I could say why. So he's really into semantic subtyping, by which he means types don't lie. What? Oh, sorry. I thought you were flicking off semantic subtyping. Semantic subtyping. Wow. And so he was saying, for hack, for our dynamic type, we can show that the types don't lie. If there's no dynamic in it, and you say something's an integer, then it's really an integer. Otherwise, something can merely aspire to be an integer, which is like squiggle integer.
So I don't see the
And so
contradiction with what I thought.
Well, what he was saying, Victor was showing all these improvements from this. Oh, you have a choice where to put your dynamic. Like your dynamic is parameterized over whether the upper part is dynamic or the bottom.
No, they both are not dynamic, but the two gives you the dynamic type, because the dynamic type you obtain, it is the lower, the lower union, the larger intersection dynamic, and there is just one.
I'll see you later.
Yes.
Thanks very much.
We should eat, no?
So my goal is to
I'm stay here the whole week, I don't know.
Yeah, me too. My goal is to have an interesting discussion about types, and I would say thanks to you.
But I'm working on this thing, so you need? Yeah. Why not? That's the first. Usually this happens with Jose Valim. In the conference, have you been in a conference with Jose? With Jose, you have all the developer. I'm a big fan. You can, yes, please. But okay, do you want them to get something?
I'm not as famous, but I can take the photo.
Yeah. Oh, okay, sure. But I'm not famous actually. Can
I have a photo with you after?
Me too.
Okay, go.
We're one of like 4 Elixir developers in Singapore.
Okay.
Actually, my hand's shaking because I was. Would you take it?
Okay. 1, 2, 3. So to Fabrica. First time in my life.
Second time? Second time?
Well, you show it to Victor. You still see Victor?
Yeah. Just socially though.
You sent it to me. Yeah, thank you.
Yeah, thank you. Thank you very much. Yeah, sure.
Thanks. You can find my name, I guess.
Okay. I will, and hopefully we'll talk later.
Yes, sure. I'm very interested.
Wait, no, I'm not sure about something. I mean, tell you what's happening. I talked to you and to you, so I talked to you. What I said, and we said everything times.
And you'll tell them that I remember the word keeper.
The three of us, okay. One, two, three.
So what's sometime I want to see how you solved this.
Yeah, we can come back here on the whiteboard. I can show you. No problem.
Yeah. At least but so you don't think, oh, you have your own special empty list, and so you don't have that problem either.
No.
Yeah, I see. I see. You asked me if I speak Italian.
Yes.
I speak Spanish, okay.
Okay. So.
Those are pretty close, right?
Yeah. Nosotros hablamos castellano.
Castellano?
Yeah, podemos hablar.
No, porque yo aprendí.
¿Estás argentino?
Español.
No.
Ah.
Yo aprendí con los argentinos. Digo
yo. Vos.
Vos. Ah, mira. I forgot my.
¿De dónde no son?
Málaga.
So, but I'm Italian, I live in France, so.
How's your Swedish?
But Japanese is improving very well.
Everyone's pretty much on the same side. It's just why we.
Okay. How's it going? Good, how are you? Not too bad. Are you a presenter or? Okay. Nice. Okay. Good.
Just try out in the morning.
Oh, yeah, yeah, of course. Actually, I'm going to stop the screen just to make sure that's still working. Okay, so you're, oh yeah, you're a 3:15. And so what was your name again? Are you, you're, oh yeah, you're, and then.
For lightning talk, that's at the end of the session.
And are you a Daniel Gorin? We have two Daniels, Gorin or first? Gorin. Gorin, that's cool, okay, so you're first. Great. And you're all happy with the streaming and recording, which makes it easy. And what do we do?
you both using your own laptops?
Yeah.
I wanted to try it out. Oh, and so you have Zoom and all that sort of stuff. You have Zoom installed and everything. Do you have Zoom?
I need Zoom.
You'll need Zoom. Because so the way that so we're not plugging into here. We have to so there's like a Zoom call for each workshop, and then you'll call into this thing.
Do you have the link for it?
Yes. So there is sorry. It's a community there. So there would have been an email, I think, yesterday as well, which has this link. So whichever's easier to access.
Okay.
Oh, good thing I mentioned it.
Once you can type in your email.
It's a funny system. This, I think, it's to make it work with the remote people as well.
I don't have it. What's the?
If you have Zoom installed, it might be easy if you just have this. So
No, but I need Wi-Fi.
Oh, right.
So
I think this
in
is
US.
stuff for.
what Wi-Fi is that?
Okay. Username.
I'm not sure I have Wi-Fi. I think.
Or is there Ethernet, something like how am I?
There is Wi-Fi. Do you not have? I guess you don't have EduRoam there.
I don't have it.
No. Oh, you're from Meta. Oh, interesting. Yes. So no EduRoam. Let's see. I'll just ask what the Wi-Fi.
Just a guest network. I don't know. I think I received an email yesterday.
It might not have been yesterday. Let me see what actually was sent out. It's possible they actually just didn't.
On the 10th.
Oh, on the 10th, that's it, yeah.
Waiting for Sunday.
Okay. So maybe
Otherwise, I can
if you-
put in my login for everyone.
If you don't have the Zoom link, it might be easier just to.
okay, yeah, sure, this is fine, but I need to connect.
You'll need, yeah. Someone's typing, so I should be able to have that in a second. Yeah. I think. Surprised it's not on the website.
Okay, I found it on
Someone's typing properly. Stop. Sorry. Don't worry, anyway, there's no rush. It takes a few minutes. Still no Wi-Fi.
No, I got it.
Oh, you got it. Oh, you got it. Oh, great.
I didn't find the email.
And you can go to the browsers and monitor the meeting. So that should take you
Where?
to just go to Zoom and you should have an option to use it from the browser.
Yeah.
Oh, do you have Zoom installed now?
I do. I know this is.
Oh, I think it was. Yeah. You shouldn't need to just sign in theory, and you can if you want to. If you, if you're able to go to that step where it was before you clicked on sign in, maybe you need to click home. Maybe okay. But then like that you can join the meeting now sign in. Yeah. Perfect. And then it's meeting. If you can do that. Alternatively, you can get your slide up on the eventually.
Sure.
Do you have no? Can you read out the link? Can you read out the link or is that crazy?
No, it's gonna.
It's not gonna. Okay. You could sign in to give me a box. Yeah. Oh. We sometimes get a link. Be a good way to do this. If not, then maybe try to Zoom by the filter. That's yeah. Oh, I'm not getting to let's say if I log into my channel, that's not I mean, I think it's everyone's fine. Yeah, sorry everyone, technical problems. There's nothing really yeah. Oh, I'll do it on the and I'll stream from that. Okay, you want to see right. That's the only bit that really no. There's a chair in this meeting. This might be a chair. Thank you.
What we did this morning was join the Zoom, share the screen on the Zoom.
Yeah, Zoom, Zoom was not working on his laptop, unfortunately, so I had to send mine, but here we go. Okay, so there, I slideshow, and then share my screen. Oh, I'll hand you my laptop. Okay. Is that okay? Oh no, of course it's not, because I'm not looking at it. Great, that should work. Sorry about the delays, everyone. That's okay. So it's recording, streaming, that's okay, right? Cool. All right.
So yeah, sorry for the delay. I'm Daniel. I work at WhatsApp at the developer infra, developer experience team, and yeah, I'm going to talk about like debugging for Erlang. Okay, cool. So debugging, how does debugging typically look in Erlang? I would say there are like 3 options. One is using tracing directly or using some library like Redback or whatever. Tracing is super cool. I like to say that it's like Erlang superpower. You take like a running node without changing any code. You suddenly get logs of stuff going around. It's super cool. It has its cons, so it works great if you're like troubleshooting something on a live cluster or live system. But not everything is a live cluster. Maybe it's like a short running program, like a test or a CLI app. And also, I mean, we shouldn't get to the point where you need to troubleshoot stuff in production, but it can happen. So if you're not using tracing, well, the other alternative thing is just put print statements everywhere. That always works. You get like long feedback loops, like you need to change the code, and wait for everything to rebuild, run your test again or whatever and see what happened. And it's a bit messy. You need to clean up things at the end before sending your pull request or whatever. And then OTP, since time immemorial, comes with a debugger application. It's like sort of traditional step debugging. This is good. Like a lot of people like this kind of debuggers. They are used to using them, especially like newcomers to the language that would like to use it. In practice, what we find is that when people were actually trying to use the debugger, they got stuck for various reasons and just give up and not use it. We, as I said, I work in a developer experience team, and there is a thing that Meta does that is nice, that it runs
regular satisfaction surveys across all engineers to see like what tools are working well. And systematically for many years, we're getting very bad signal regarding debugging. One typical comment that they will say is like the Erlang debugger always times out. What this means, if you try to decode, is people would, let's say, put a breakpoint on a handle call from a Gen server and then run their test or whatever. The process executing the handle call pauses in that breakpoint. The user starts inspecting variables and whatnot, but the caller of the Gen server had a timeout of whatever, 5 seconds. So by the time the user ends and decides what to do next, the rest of the system already timed out and crashed. And in a way, like their debugging session was ruined. So our first impression was that if we wanted to solve this thing, we need an Erlang debugger, a step debugger, to stop the work, like not just the process that hit the breakpoint, but every other process on the VM. So we could say, okay, let's take the debugger that exists, the debugger application that comes with OTP, and extend it so that it does this stop the work thing. Now, we didn't think that was a good idea, a bit because of the way this debugger works. So if you're not familiar with it, the way the debugger that comes with OTP works, what it does is if you set a breakpoint on line 42 in function foo, what it's going to say, it's going to ask the VM to hijack the execution if function foo is ever run. So instead of running the actual code, the execution goes to this Erlang interpreter that will load the syntax tree of the module and start interpreting it. Because it's interpreting it, it can know the value of all variables involved, decide if it needs to stop on a breakpoint step or whatever. But like, let's say we hit a breakpoint and let's say that we manage to pause every process on the virtual machine. The interpreter has no idea what's going on with the rest of the processes. Like we cannot say like what was the state of the caller, like what were the process that called the current Gen server or whatever. Like we would be blind. So we decided to embark in an adventure to try to replace the debugger that comes with OTP with a new one decided to provide like good visibility about everything that's going on. The main changes, I mean, the main components of this were changes to OTP itself. We needed to extend the VM with new debugging primitives. We needed to extend the compiler to have like some kind of debug mode where it emits more debugging information on the VM files. With those, we wrote like a new debugger, like an Erlang application that gives us like all the common primitives on a step debugger. And on top of that, what it's called like an adapter layer. It's like some kind of front end for the debugger that can talk a protocol that most IDEs can understand. So we can use it with VS Code, Emacs, Beam, IntelliJ, whatever. So the rough architecture is something like this. The user is using their IDE, whatever VS Code. They launch a new debugging session. This creates a new node, which we call the debugger node. This thing is talking through this adapter protocol with VS Code to decide like which set a breakpoint, to get some variables, whatnot. And it also connects via right now Erlang distribution to the node that is actually going to be debugged. This could have been a running node, a node that was already running in the system, or it could be a node that is launched as part of the debugging session. And connecting, what it means is the debugger node using distribution will inject support modules on the debuggy node. and it will start a special gen server, what we call here the debugger process, that will use this API provided now by OTP to control what happens in the execution of the node. And then the debugger node controls the debug via this debugger process. So yeah, let's see how things more or less works. What were the changes that we needed to make? Let's begin with breakpoints. If we want to have breakpoints, the first thing that we needed to do was extend the compiler. So the Erlang compiler now has a new compilation option, a flag called beam debug info, that if you program with GCC, it's similar to using -g in GCC, like saying like I want to have like a debug build. This does a couple of things that I'll discuss next. The first one is that a new bytecode was introduced, debug line, and the compiler will emit this line on the bytecode at the beginning of each executable line. This is similar to other instructions that the Beam already had. There is one called executable line that is used for connecting coverage. There is one called line that is emitted at fewer locations, that was for being able to reconstruct in the stack trace what are the colors at each point. This one is similar. It is emitted at the beginning of every line, but it needs to provide more information. In particular, it needs to provide how many registers are live at that point, because the VM is going to need to save them, stash them in a new stack frame, make it safe. And the compiler also ensures that at this point, it's always safe to deschedule the process, which means ensuring there are no gaps. So all pointers are safe, are well defined, so it's okay to swap out the process. Next, we needed to extend the VM with support for this. There's a new flag for the Beam called class D for debugging. So if you have your source file was compiled with the new Beam debug info, and you are running it in a Beam that was started with the class D option, then when let's say the just-in-time compiler is loading a module and it finds one of these instructions like debug line in line 42 or whatever, it generates something that looks like this tiny snippet of code. The important things are it emits an unconditional jump to this block here, and in between it adds a few instructions. So under normal conditions, there is an overhead of one jump, and these things are ignored completely. And it also takes a note in some internal table the Beam always had of where in the code line 42 starts. So with that, we can then add a built-in function to toggle a breakpoint. What does toggling a breakpoint mean? If the caller says I want a breakpoint on line 42, it first needs to check this line table to find where in code, what's the offset in code where the line 42 starts. It knows that there should be a jump here, and then it mutates the code. It replaces the conditional jump by another unconditional jump, but this time it sends it to this small block. What this small block does is, puts in a register the number of Beam registers that we need to save on a stack frame, and then run some common logic that will create dynamically a stack frame, save all the records, put the process in a waiting state. and send a message to this debugger process that was registered as the debugger for the node. This, by the way, is except for the part where we need to create a stack frame on the fly, is the same infrastructure that drives, let's say, tracing. For tracing, something very similar happens, but at the beginning of the call, beginning of the function, here we need to be able to handle it at each line. But most of the infrastructure likely was already there on the Beam. So yeah, with these two things, we get, yeah.
So is this debugger primarily implemented in the source to bytecode compiler, or is it kind of that plus the engine is aware of the?
It's a combination. So there's, for breakpointing, we are using this support from the module loader. We had to add another built-in functions to be able to inspect registers that I will discuss in a couple of slides. And these are like very low-level debugging primitives. And then we build the full debugger as an Erlang application on top of those primitives.
Okay, so you like have more exposed functionality in the host that's being used by the debugger.
Yes, okay. Yes. So with this, we have enough to be able to set a breakpoint and get a process on a waiting state and a message sent to a debugger. Then there's the part about like stopping the world. Here we see like what you would see on, I don't know, VS Code. When a process hits a breakpoint, this is a view to show like shows every process, and you can do the stack and whatnot, but you see that it says that they are post and one is post on a breakpoint. So conceptually, even though like stop the world is in the title of the paper, it's like the easiest part, because for a long time, Erlang had like a suspend process if that would mark the process as not to be scheduled until you resume it. So conceptually, when something hits a breakpoint, the debugger can just call this function on every process running. There's some details, but it's mostly it. The thing is, that would not have been enough for what we wanted to do, because this problem. So suspending the process was only marked as do not schedule. But we have the problem with receive statements and timers, the one that motivated this problem. So internally, this is an implementation detail of the Beam, but when a process starts executing a receive statement, the first thing that happens is that if it has an after clause, a timer is set for 5 seconds. And it will check if there is something in the mailbox, and if there's nothing in the mailbox, the process will be descheduled and be in a waiting state. And what can happen is that a message arrives and it's processed, and if it's processed, the timer is canceled, or 5 seconds pass, the timer goes off and sets a flag in the process saying like timeout. And the process will be scheduled once again, and because the timeout flag is there, execution will continue here. So suspending the process is not enough if we don't do also something with the timers. And so we had to extend the suspend process beef to deal with it. Conceptually, this means when suspending a process, we need to check if it has a process timer, stop it, but take a note of how many milliseconds remaining, so that when we resume, we create a new timer for that amount. And yes, with this, we can give this illusion that the node is stopped. As I said, ideally, we would just suspend every process except the debugger process. In practice, this doesn't work because we are using distribution to connect the node being debugged with the debugger. So if we kill every process, if we suspend every process, the distribution connection goes down, and then the node will be bricked effectively. So we use a heuristic. We suspend all user processes. The current heuristic is if a process is in the current application, we exclude it, and there's a couple more system processes that need to be excluded, and everything else we suspend. This, for now, it's been working well as a heuristic, but it's user configurable, so for settings where this doesn't work, it can be changed. And then the question is how we suspend them. Right now, we did the simplest possible thing that could be done, that is list the processes, go one after the other and suspending, no concurrency, nothing. In fact, when we try to be a bit smarter and use like an asynchronous option that exists where you can like suspend the process, but not wait until it's effectively suspended, results were even worse. So for now, the latency is acceptable. I think it's working well, but there's room for improvement. So yeah, inspecting variables. So what we want to be able is to show what are the value of the variables in the running process. I won't go into a lot of details, but just need to know that in the Beam, in the virtual machine, there are two kinds of registers, what are called X registers, which would be like what one would call a register, any kind of register machine, things that ultimately tend to end up in an actual processor register. And Y registers are just a name they give to slots in the stack frame. So we have given stack frame, they are numbered 0, 1, 2, 3, they're called Y registers. So this new Beam debug info option that was added to the compiler makes it so that it creates a new section on the Beam with debugging information in the way of a table that says the beginning of line 42, variable foo is stored in X3, and variable bar is stored in Y13. And we, on top of that, we added built-in functions to be able to pick the value of any X register or Y register in a suspended process, and do the same for all the contents of the stack. And that's mostly it. So with this, we can set breakpoints. Something stops, we pause the whole VM. We can show the values of the variables, show the stack. Now, the user wants to step into, like, what do we do? I think we would have two alternatives that I can think of. One is to make the VM aware of stepping, like add some kind of flag to the process where a process can be in a stepping state, and in the next call or whatever, it tells you something. I thought at least that would add a lot of complication and probably performance issues in the VM. So the next thinking is like a C debugger or something like GDB, like it only has a breakpoint instruction that the CPU gives it, and with that, it simulates everything else. So let's do the same. So stepping is simulated at the level of the debugger. I mean, probably this was long known for 50 years, but I never thought before how you actually implement stepping based only on breakpoint. So it was fun to think about it, but I mean, it's not nothing very new. The idea is, well, first, you need to have some bookkeeping to know that some breakpoints were set because the user wanted, and some breakpoints are set because certain process is currently stepping. So that's some kind of conditional breakpoint. We currently don't have any kind of debugging information that tells us at each line what is the next possible lines where the control could flow. We just over approximate and set these funny breakpoints on all the lines of a function. That's been good enough for now. Then we also need to consider the callers of the functions that are in the call stack. because maybe when you step, you end the execution of the current function and you want to land in the caller. So you need to set a breakpoint in the function of the caller as well, just considering this. And when you're stepping, also the function could raise an exception. So you need to identify along the stack where the exception handlers are that we can, with this if we add it, and set breakpoints on those functions as well. And then it gets a bit tricky when you do things like you want to step over on a recursive call and you don't want to enter the recursive call. So how are you going to tell apart these two cases? How do you know if you are stopping on the right frame? So you also need to keep track of what you expect the stack to look like when the breakpoint hits for you to stop, so that you make sure that you stop at the right point. So that's mostly the idea. Then for stepping, so this covers stepping over, so ignoring the current call and just go to the next line, and stepping out. For stepping into a call, you sort of need to know what's the call target so that you can set a breakpoint in that function. We did two approaches. Initially, we were using the abstract syntax tree to figure it out, but it is a bit of a mess, and we are essentially redoing the work the compiler does. So we extended the compiler so that it adds this information at each line, which are the possible call sites as debugging information. And we can in principle support dynamic calls as well, because we can know that a dynamic call involves variables and we know the values of the variables. Okay, so something I didn't mention so far. There is a cost to this. The cost comes from two places. One, the overhead of these mini trampolines, which I expect was going to be negligible because it was being used for tracing anyway. And the other is when you compile something with this beam debug info, in order to be able to keep track of the value of the variables, it needs to disable some optimizations. I'll discuss one in a moment, but like one set of optimizations that are disabled right now are, I think, all the ones that have to do with binary handling of binaries pattern matching, etc. This is because optimizations were not keeping track of where the variables end up, or they might end in multiple places or whatnot. So we just turn it off. And the question is good enough? Like, will everything crawl to a halt? So, of course, if you do a benchmark on code that, let's say, does a lot of binary processing, the numbers are going to be terrible, but it is expected because that's why the optimizations were introduced in the first place. So, but if you look at more realistic code, what we did as an experiment is take a very large number of real tests used at WhatsApp, and there were like 2.5 days worth of execution, one after the other, and ran them with and without debugging compilation and see how long it takes to run these 2.5 days of tests. And the difference in practice was quite good, right? What this means is that all the overheads are in practice in message passing, input output, etc. It's not really an issue, and we've been using this debugger since the beginning of the year, and people are happy. So I assume that it's not really a big of a problem. Okay, so this was a longish project, and you really want to get to something that works quickly, and you need to take some shortcuts along the way. So let's discuss the shortcuts that the main ones that we took and what we do. So I said, for instance, that we have like debug information that says at the beginning of each of this line, these are the variables that are available. And we use the line, we could have used line and column because that is the granularity the compiler gives us, like the compiler annotates its expressions with line or line and column. But it's not true that every line, the code for every line ends up in a single place in the bytecode. Like the easiest example is function inlining. Like if you look at line 42 of a function that gets inlined multiple times, well, line 42 will end up in multiple places, and the context in each place is going to be different. Where the variables are going to be located, it's going to be different. So how do we support this? Well, right now we can't. So no function inlining when compiling in debug mode. There is a similar example with comprehensions, like generators and matches get compiled in different places. So you either say that the beginning of the line is when the generator is executed or on each match. Right now, I think we do it on when the generator is executed, which means that when you are stepping over code with comprehensions, it looks a bit weird because the execution never goes back to the match. How to solve this? Well, we need the compiler to have some finer notion of for each expression, we need some kind of, I don't know, like an expression ID, and then maybe multiple expression IDs mapped to the same location, but then the VM needs to be able to deal with those expression IDs as well. So it's doable. It will require a bit more work. And slightly related to this, for me, it's like the other, like almost the same problem. When if a process is paused, we want to see the value along the call stack, like what were the variables of the caller of this function. We can show the value of the registers, but we don't have a way to map it to a variable because the information that the compiler gives us tell us what were the variables stored at the very beginning of the code for that line. But by the time the actual call happened, things can have changed already, and that information is not accurate anymore. So we cannot show it. We need some way to give this information almost by expression, not just by line. And if we can provide this information per expression, it would be nice if we can have like the ability to set breakpoints per expression, not only per line, because then stepping can be done in a more granular way. Conditional breakpoints, we use them only for stepping right now. They're a bit slow, essentially because the evaluation needs to go through the debugger process, and that becomes a bottleneck if you are doing this on a hot path. Ideally, we should be able to evaluate this on the VM itself. And there were some other issues. I won't go into details. The most annoying one now it's fixed, which is that we were not, like the compiler is very aggressive, naturally optimizing variables that are not referenced anymore. But then it would mean that when you hit a breakpoint, the user wants to see what were the arguments to the function, what is the variable mentioned in the line above, and they were not visible. Now, for next version of OTP, there's going to be a flag to relax this condition. Like it's a trade-off in memory usage, but we've been trying it out, and it looks to work pretty well. And yeah, I think that's mostly it. So the OTP extensions, most of them made it already to 28.1. Some are still in a pull request state, but we hope they're going to be merged soon. And anyway, the EDB debugger can work on like with only those extensions merged. So this is good. This is available on GitHub. People can use it. The easiest way to use it is if you are a VS Code user. There's a like the Erlang language platform is an extension for VS Code that my colleagues at WhatsApp build and maintain. This comes with equalizer and whatnot. It's a super nice extension, and now it comes with the debugger as well and some convenient to be able to launch tests and have them run under the debugger. So yeah, I think that's funny. Thanks for attention.
Let's see, we have 1 minute left. In case there are some questions.
Yeah. What kind of feedback did you get from your users? I imagine it must be interesting because they're used to using things like tracing.
Yeah, so they were not using tracing locally. I think it was print statements or yeah. I think so far it's been happy. I get perception in the last survey went up. So far they're happy with the results.
And tracing you could use perfectly in production, but you cannot use CDD in production.
I mean, you can. The question is if you should.
But you will need to reload again the module, so do the hot code swap.
Yeah. Yes, I mean, yeah. In principle, there are workflows that could be done. Like you could change things so that the work is not stopped. If you have like some, or change the logic to what you stop, not to stop everything, but some connected component of your process or something like that, and load only fewer things.
Thank you. Great. So the next presentation is going to be remote by Daniel.
Yes, can you hear me?
Yeah.
Oh, yeah. Perfect, thank you. Let me just turn on my camera and let's see how screen sharing is working.
Can you lower the sound? I mean, because I think it's a bit.
Oh, I see what you mean.
I think the volume.
Not. Wait.
It's not. That's how it is.
Okay, I think it is set up now.
Seems good to me. Yes, I think is that all right? Cool. Okay, so this must be the right screen. Screen.
Perfect.
And your.
Okay, I had some trouble hearing you.
That's probably okay. Can you hear us at all? Oh, maybe not.
I can hear you. Not very well, but I can hear you.
I'll see if I can sort out for the questions. Just one thing. Can I make sure like you're okay with this being recorded and streamed? And all that. Is that?
Absolutely. Yes.
All right, great.
Yes, of course.
Okay, well, all yours then.
Thank you. So, hello everyone. My name is Daniel Ferenci. I'm a PhD student, and together with Gergely Ruda and Melinda Toth, we have been working on an evaluation of using AtomVM for adding fault tolerance to ESP32 based systems. So we have started this research as we were interested in how some aspects of developing and operating IoT systems could be improved. IoT systems have some distinguishing traits. They are distributed by definition. They use multiple devices that have different roles across networking tiers. They should also be scalable. We should be able to add and remove devices, especially sensors that might be deployed on the field as effortlessly as possible. Also, as the system, perhaps even the applications are distributed and heterogeneous, testing can be difficult. The whole system might be based on different technologies across the networking tiers. And finally, devices might use different types of hardware, ranging from microcontrollers to servers. Many of these characteristics we found to be in line with Erlang's highlighted features, like fault tolerance and language level support for building distributed systems. If practically would make many of the aspects of IoT development easier, ranging from the design of a distributed application to simplifying the software stack using the complete system. But supporting the variety of hardware that can be present in a complete system still requires some additional work, however. As hardware in these setups can range from powerful servers with gigabytes of memory and multi-core processors on the higher levels of a setup to simple microcontrollers with only a few kilobytes of memory on the field level. They also differ in how much power they require to operate. Some use cases may require field-level devices to work on battery power exclusively. Using Erlang in IoT is now supported in 3 projects: NERS, GRISP, and AtomVM. NERS targets devices in the range of Raspberry Pis or BeagleBones that typically run on continuous power and may have hundreds of megabytes of memory. NERS provides a specialized distribution of Beam on a stripped-down operating system that is specialized for these devices. GRISP, on the other hand, runs on specialized hardware and brings Beam as close to the hardware as possible to allow a tight integration between the runtime and the device's real-time operating system, and this allows hard real-time event handling. AtomVM is very different in this regard, as it is a reimplementation of Beam, targeting very low-powered microcontrollers with memory in the range of a few hundred kilobytes, and these may even run on battery. We are particularly interested in what we can achieve with embedded devices with memory in the range of a few hundred kilobytes. Therefore, we chose to look at AtomVM in more detail. AtomVM is still a work in progress, and while it lacks features of complete Beam, it still allows typical features like running hundreds of concurrent processes in those few hundred kilobytes of memory your device may have. It allows monitoring them. You can construct OTP behaviors, and it provides an Erlang interface for working with the hardware's features. Supervision trees, lightweight processing help build fault-tolerant applications for single devices. Multiple microcontroller families are supported, but we did our experiments on the ESP32 development boards. So ESP32 is a family of microcontrollers, which made this choice as AtomVM has the highest level of support for this board. This includes general purpose I/O, which is practical for interfacing with any sensors that we might put on the board. This includes universal asynchronous receiver transmitter, This made sending and receiving data to the board through a serial communication easier. This is useful for our experiments. And a networking stack lets us experiment with applications and hardware sending data. And in total, these interfaces help us send data, read outputs easily. Finally, we also have LoRa. That is a long-range communication technology that is popular in IoT systems. This helps us experiment in scenarios where we are using a communication technique between devices that could be used in some real-world use cases. Altogether, these features help us tailor experiments similar to what can be seen in the real world. So we chose the S3 version of ESP32. This hardware in particular includes 512 kilobytes of memory, a dual-core processor, connectivity options through Wi-Fi, Bluetooth, and LoRa. It can also be put to deep sleep. This is a state in which a device barely consumes any power. Using deep sleep when the device has no task to perform allows reducing the device's power consumption and prolong the time it can run from battery. And finally, the devices are also supported by the Arduino IDE. This allows us building C++ applications for them easily so that we can compare the performance of an Atom VM Erlang application to that of a traditional implementation quite easily. So apart from the features Atom VM we already highlighted from Atom VM, some recent development releases also include partial support for the distributed Erlang protocol. This lets us send and receive Erlang messages in a language-native way between devices, even with computers running real beam. Doing process monitoring between the devices is also supported, but we do have limited connectivity options as not all features of distributed Erlang are implemented yet. Our goal was to add fault tolerance to an ESP32-based system using all these features we have highlighted from Atom VM. In a typical IoT setup, we have some powerful server nodes on the top tiers. Gateway nodes are connected to these servers and they receive data from a potentially large number of sensor nodes, typically through some sort of wireless communication method. We wanted to add fault tolerance to the gateway nodes in such a system. We found them interesting as the failure of such a component can lead to data loss in the complete system. So let us start by looking at a non-fault tolerant system to which we later add fault tolerance. We start with what we refer to as a gateway. This is a LoRa server and it has the purpose of receiving LoRa frames from field devices. These client devices are sending data wirelessly through LoRa continuously to our server. Finally, our server is connected to a PC to which it can forward the data it gathers. It also lets us collect the server's memory metrics so that we can see consumption, any bottlenecks, any adverse effects that we provoke with our configurations. And we can change the configuration as well on LoRa server according to the experiments we are performing. The LoRa server here is a point of failure, as in the case of an error, we can't gather data from the clients anymore. So to add fault tolerance, we should start by adding a second LoRa server. But now we have the challenge of only running the LoRa receiver process on one of the servers to avoid any sort of data duplication. And we solve this at the moment by running a Beam node on our PC. This node manages LoRa receiver processes on these LoRa servers. It keeps track of servers in the system and ensures that a single receiver process is operating at a given time. The management node checks server processes using process monitors through distributed Erlang, and the messages that trigger the activate and sends messages that trigger the activation of LoRa receivers also through distributed Erlang. To summarize, our system has 4 types of components. Client nodes send data periodically through LoRa to a server node. The server node capable of receiving data is selected by the management node. The memory consumption and overall performance of the server nodes is followed from a developer PC. Client and server nodes run LMVM on an ESP32 hardware, while the management node runs Beam on a PC. The management node and the servers communicate through distributed Erlang. We do fault tolerance by a logic that detects failure of the LoRa receiving process and activates it on an idle server. As our fault tolerance implementation is based on distributed Erlang, our main goal was to test how robustly distributed Erlang works on these devices. The server nodes receive LoRa frames every 300 milliseconds or 500 milliseconds continuously, depending on our configuration, as this is their main role. We chose these rates for receiving messages, as a single server node acting as a gateway might receive messages frequently if there is a large amount of clients sending messages in the deployment. We check how running additional processes causes instability for LoRa frame reception, and whether any instability can be detected from the process monitors on the management node. We tried 2 types of loads with additional processes, reading voltage values on a given pin of the device. We chose this to be analogous to interacting with additional sensor components that could be added to the real device. We also experimented with adding computationally more demanding tasks, like verifying whether numbers of different sizes are prime. In a base case, where the server only receives LoRa frames without doing any additional work, we tested fault tolerance by simply powering off the active server. Absence was detected by the process monitor on the management node in a few seconds, and the management node started LoRa reception on one of the idle servers. In total, a backup node took over LoRa reception in about 5 seconds. Adding any sort of additional work, however, slowed down processing LoRa messages. This could be noticed particularly well on the 300 millisecond configuration, and where data here was not lost by default when we were not running any additional work. Even adding a single additional process resulted in the node losing data. On the 500 millisecond configuration, we needed to add about 4 processes to make data processing unreliable. And by unreliable, we mean that our server node started losing data, and we found that they became so overloaded that if they were not added to a distributed Erlang configuration from the start, they were not we could not add them while they were overloaded. If they were added beforehand, however, we found that the receiver processes appeared healthy from monitors on the management node, even though for all particular processes the node was absolutely unreliable. As a summary, LMVM requires about 250 kilobytes of memory, while starting distributed Erlang increases this to 32 kilobytes. A heavy load on a system like processing wireless messages that arrive frequently causes the node to become unresponsive, unstable in practice. These problems might not surface through monitoring. We kept adding new processes to an already unstable system to find a point at which the monitor detects any problems with the server node. Eventually, after adding about 200 additional processes, the system became so unresponsive that the watchdog restarted the complete system. And finally, the management node detected that the monitoring process was missing and restarted it on one of the idle boards. We concluded that aligning the watchdog with the workload that is to be expected on the device is still required if we want cross-node process monitoring to react on practical node responsiveness. Altogether, we were only able to start additional processes when receiving data at the rate of 500 milliseconds. But even in this scenario, we were only able to start 3 lightweight processes that checked the voltage or verify the 4-digit, or verify whether a 4-digit number is prime. This work is part of our ongoing research in finding industrial applications of Erlang, especially in the domain of precision agriculture and industrial automation. For this work, we want to explore different device onboarding flows. Ideally, we would want server nodes to connect to a central server autonomously. We were not able to do this in our current experiment because of some limitations on how distributed Erlang was supported on AtomVM. Perhaps we would even want to do in the future process management on the server nodes without the need of a dedicated management node. We are following the development of distributed Erlang features on AtomVM to see how these expand our options. This would also help us run distributed Erlang applications on embedded boards. We also want to experiment with aggregating data on the client or server nodes. Such experiment would fit IoT and would highlight how Erlang helps building concurrent applications that perform different tasks, even on embedded devices. Aggregating data locally, especially on sensor level nodes, will also be a fitting example of using Erlang processes to easily add encapsulated features. Altogether, in our research so far, we measured that 512 kilobytes of memory can host hundreds of lightweight processes. We can use these to build applications in the OTP way with behaviors. With distributed Erlang, we can manage processes between nodes and build fault tolerance around this, although we should account for any expected load on the system. As opposed to using Arduino IDE and C++, we found fast compilation times, dynamic types, and pattern matching very convenient for iterating our software fast. And with that, I would be very happy to answer any questions.
Thank you very much. Well, I'm not the chair, but I'm at the front. So I guess if there are any questions, hopefully the audio will come through. Yes. It looks like there are no questions. But yeah, well, thanks very much for that. Oh, wait, we have something in the chat. Oh yeah, that was just someone saying we can hear. Yeah, fantastic. It's coming. So let's see. So you can get. Oh, if you you don't plug it in, but if you just connect to the Zoom thing and then share the group, then that should
Okay, so I don't need to connect.
no. Apparently that breaks it.
Okay.
At least audio wise. And you're okay with it being recorded.
Okay. Hello everyone. I'm Laura Boina from the University of Glasgow. So today I'm going to talk to you a bit about Mailboxer, which is a prototype tool that we've developed at the University of Glasgow as part of the Stardust project. And Mailboxer is a tool that uses mailbox types to statically detect communication errors and Erlang. This is joint work with Duncan, Simon, Daniel, and Phil. And Duncan has been the main developer of Mailboxer. Okay, so actor languages, and in particular Erlang, has been very, very good at building scalable and reliable distributed systems. However, as any other language, it's still prone to communication errors. And here we're going to use a simple example of an ID server to highlight some communication error classes. So this is a very simple example given an Erlang-like pseudocode. And on the left-hand side, we have an ID server which receives an init, and the number goes into a forever loop where it receives GET requests from a client and then sends an ID with a unique number. And on the right-hand side, we have the client that spawns the server, sends an init message with a number 5, sends a GET and its PID, and then receives an ID tag and the number and prints it to string. Okay, so what can go wrong with this very simple example? Well, we can have a payload mismatch. So say we have, on the right-hand side, we send a string 5 rather than a number 5. Well, that's the wrong type, and that's going to lead to a crash. What else can happen? An unsupported request. So again, say on the client side, we mess up, and instead of typing GET, we type GT. Well, that's wrong type. And that's going to lead to mailbox jump, not necessarily a crash, but a silent error there. What else can go wrong? Well, an unexpected request. So say once we've sent the initial init message, we send a second init message. That's going to cause a crash on the ID server side, which only expects one init message. We can also have an omitted reply. So say the client simply doesn't send the ID. The server, simply doesn't send the ID. What happens then is that the client gets blocked, it keeps waiting on ID forever, and that leads to a crash on the program. Well, communication errors aren't exactly cheap. They lead to defensive code bases, defensive codes with bloated code bases, extra maintenance for the extra code. Can lead to late discovery of these communication errors with processes crashing at runtime, blocked processes, or mailbox junk. And our goal here is to fail fast and fail early, detect as many of these errors at compile time in the development process rather than waiting for it to crash in production. So here come mailbox types. These are a novel behavioral type discipline, first introduced by Ugo Del Guro and Luca Padovani in 2018. And they are very much targeted to actors and to representing the pattern where you have multiple senders with one receiver being the mailbox. We have mailboxes that describe this interaction. And in here, there are first-class entities that are typed themselves rather than typing the processes as you would have with different behavioral types. And the process interaction is then implicitly captured via the mailbox state at any given time. Later on in 2023, Fowler et al. Introduced PAT, which is core programming language with first-class mailbox types. And the type checker from PAT is what we use in Mailboxer as the backend. So mailbox types are represented by a capability and a pattern, where the capability is either bang P, where P is the pattern that represents messages that must be sent, or question mark P that represents messages that a mailbox can contain and then must be consumed. And the patterns are commutative regular expressions that describe the configuration of messages in the mailbox. They capture out of order message deposits. They capture selective message reception. And for example, if we think about the ID server that we saw previously, receiving one init and many get messages is represented by this question mark init dot get star, where star means 0 or many get messages. Send one ID message is represented by bang ID, and receiving many get messages and one init messages is represented in the same way as previously with question mark init dot get star, because it's a commutative operator. So mailbox types promise us tool that can work at compile time, so we can get early error detection, eliminate some of the defensive code around communication. It promises us a tool that can execute fast and is usable during development. We can annotate the code with type annotations to represent the mailbox types, which also lead to documenting the developer intent in that code. Something that is compatible with existing tools and available, and something that scales. However, it's not that straightforward to apply mailbox types to Erlang, because in mailbox types and in PAT, mailboxes are first class, while in Erlang they are monolith. So what does it mean that they're first class? Well, processes can create and free mailboxes at any time. They can own many mailboxes and they use the mailbox ID for receiving. While in Erlang, we don't really have that. The mailbox is tied to the process lifecycle. One process owns one mailbox and they're implicit when receiving. They kind of act as a bag where you have messages that are coming from different protocols all in the same mailbox, which means that if you try to track them, that's very quickly becomes very difficult, and you also get type pollution with different protocols maybe having access to type information that they shouldn't. So for that, we use interfaces to isolate the mailbox type and the state. So an interface we can think of as a set of messages that the mailbox can receive for that protocol. It gives a partial view of the mailbox, again, for specific to the protocol, and we use it to annotate the function, the specific process functions. This means that we get to isolate message types and type check them against interfaces. This approach minimizes type pollution. And we can also reason on the states by considering the smaller message set. So here I'm gonna go to a demo. So if you want to follow along, scan the QR codes and we can have a look together at the example and try to fix some of the errors that we encountered earlier. So this is mailbox or Sunbox, kindly built by Phil's master's student, Zubair Khalid. So I'm just gonna switch to that. Is the sharing still working? Okay. Okay, so let's revisit the ID server example and have a look at the mailbox types that we use for it. So we start off with defining some types for init, for get, and for ID here. So init is a tag that will also carry an integer. Get is the get tag, and we have the ID client mailbox here, and ID is an ID tag with an integer. Later we see the messages that the ID server mailbox can receive. So get PID, init, and get. And the client mailbox can receive, which is a PID and an ID. We also associate these interfaces with the functions that will use them, either using the new modality for when we use a new mailbox, or the use modality. So that's going to be the continuation of ID server mailbox. We also need to annotate the receive parts with what we expect the mailbox content to be at the time that we are going to receive using it. So for each of the receive, we annotate the mailbox with what we expect it to contain in each of them. And we can also run this example. Okay, type checks. So let's go to can you fix these? So this example contains all of the errors that we had before. And if we run mailboxer, it's going to give us an error. So it's going to say message tag GT not supported by interface ID server NV. And indeed, if we go to that, well, that's not really supported. It's looking for it yet. So how do we fix that? We go to message tag, fix it, get, let's run mailbox again. And we have a new error. This time it's a type mismatch error, expected int but got string. So I believe that this is for sending a string 5 rather than number 5. So let's fix this one as well. Okay, so that error has disappeared, but now we get a different error. Inferred message pattern is different than the one that we've asserted. So rather than being 1 init message, we have 2 init messages. So right here you can see that we're sending a second init message, so we can get rid of that. Run mailboxer again. And we still get an error. So inferred expecting, okay, produce the message pattern ID. So this is because we are not sending ID. No. And now if we run mailboxer again, hooray, it's successful. Now, I know this is a fairly simple example, but if you want to have another look at it, there are a few more working examples here. So these come from the Sabina benchmark. And if you want to have a play with the tool itself, have a look at the code, you can go to the about, go to the original mailboxer, and you can have a look at the implementation and all of the examples contained therein. Okay, let's go back to slides. Okay, so to sum up, Mailboxer is a static tool that implements mailbox typing for Erlang code bases. It embeds the communication model in the code using annotations that represents the mailbox type interfaces. This also documents the programmer's intent when writing the code. And what they thought the communication pattern should be between the different processes. Now, something that I've not shown in this demo, but you can have a look at if you want to, and the repository is that it scales to specify multiple protocols. And it's also compatible with other tools such as dialyzer, equalizer, etc. Okay. As for development plan, we're working on supporting more of the Erlang syntax, such as lists and array tuples. For longer term or medium term plan, we plan on adding pipe and pattern inference to have less verbose mailbox types, especially in the case of multiple protocols. Also planning on adding gradual typing to it to allow it to work with partially annotated code bases. And obviously, a big goal is to have it working for OTP. Okay. I think that's me. Thank you.
Yeah. Since this basically like documents protocols, like you said, have you thought about using this to generate fuzzing or like mocks for client and servers?
I mean, that would be a very interesting thing to do.
Yeah, I think that would be like really, really cool and powerful to do.
Yeah.
Okay.
So what will be the main challenge when you wanted to scale your type checker to the full scale of Erlang language? That is the one question. And the second question is that actually I'm a big fan of Haskell compiler, but sometimes Haskell compiler GHC produce type error message that misread the location of real type error. So in your experience, do you have any have you any attempt to do research on producing more kind error message related to the communication, something like that? So that is the second question.
So for the first question, that is a lot. So those are that is a very big task. So some of things that I've already listed under the development plans would be milestones to get there. So again, we're still only supporting a subset of Erlang, so we're working on adding more of that, and we're also going to work on trying to support ODB, but that's still a bit away. As for good error messages, that's a good question that I've not thought about very much. So Duncan is the one that has implemented that, and I'm sure that he would be able to talk more about it. Yeah, I don't know.
Thank you.
Thank you. Yeah.
There's no need to bring mailboxes as in path into Erlang, right? So with this interface that you described, we don't need to bring mailboxes as a value because it's self-contained in a self-process.
So what's happening is that at the moment we're using the same type checker as for that for mailboxers. Now that could be re-implemented in Erlang if we wanted to, or a different one could be swapped. At the moment, that's very useful because if we do an extension and path, it's something that we can reflect in Erlang and vice versa. So that's sort of how. Yeah.
Sorry, you spoke about variable typing, and you said that because you want to type code that is partially typed or not. I was wondering about variable typing, but for mailbox type. Sorry, in the sense that can you just say, okay, I want to specify not all the mailbox, but just a few ones, and have something like dynamic for the content of. So is it possible to introduce this mailbox typing gradually also?
So that's in the future plan.
Okay.
So yeah, that's something that we want to do. Realize that's not everyone's going to put in the effort to add mailbox types to their entire code base. Or they might not want to add mailbox types in their code base, but again, that's not something that we currently support. It's something that would be quite nice to do.
And what would be the difference with respect to gradually typing the programs? I mean, or just too early to answer?
Sorry, I didn't catch the last thing.
Or is it too early to have a number now?
No, I think it's a bit early to have an answer now. Yeah. To be fair with Mailboxer, we do very much focus on the mailbox typing aspects, and we leave the rest of it to other tools. We kind of see it as something that can be used with the rest of the Erlang tool. Well, thank you very much.
And even integrate mailboxes. Fine, because I think at some point when we have early discussions. When we have mailboxes, which is the mailboxes are. Because the self, in case in case. No, but sometimes someone has said if we would be willing to ask maybe just one, and we would not enhance, but I don't see.
That's really cool, but I don't. The most maybe if they can on this.
Not how long would you estimate the work available? Part time. Because essentially that can be work. Really? It's the paper is it's a paper.
Yeah.
Information is paper.
The same said you're not.
That's
Another paper. This has one for something more. Implementation. Paper that's.
No. I admit the one that is 50 pages.
Yeah.
And I.
The archive.
Yeah, and now I think I understand it, but it has way too many steps. And we don't have even validated for separate. And you have it already immediately. Because but there are many intermediate steps. You also need to have a type checker. It's a stupid thing, but you need to, right? And you need to support not only this and couple. So it's a lot of small changes that need to work. And if we could use equalizers to start with and remove some of the ideas that are needed. And I was going to check this user if I can give equalizer a module and it produces all the type specs. Because that's something that I actually got.
You want an annotated version of the.
Yeah, I want to give something that is not annotated and or the public interface is annotated but not getting.
I'm pretty sure that it can do that because.
Because then I can take some of the work to move from programs in the project. Because that's something that I can do myself, but again, it's a lot of time. And I want to spend time on the other bits, not on something that can be solved. So. So the net of India or Victor. No, right, yeah, well, I guess I can talk to them.
Everything starts to work. Like it's like on the correction that's there. Has been traveled cloud. The chance of code and trust whatever you say. There's no connection between the features. I think that is even though it's
See what exactly message is.
You're already like revealed your spec. Yes, I look at it. What's the and this which you expect.
Yeah.
Response, what you expect. There's nothing so to do this.
Some of it
Yes.
Yeah, so ideally, once you already provided.
In the example, I can do it like for function or because I can multi the case and like because I looked at these as an example and I think all of them have price specs for the because based on the paper, the inference that they do is based.
So.
And that's why they need to do the pre-type thing as I respect and then the other.
I mean, so it's more. The near future will start having some type of developments in place. To get rid of potential applications, I'm not sure whether you can get rid of or should have you probably want to that they're more
Yeah.
Thanks.
I also the conceptual approach to look at the types. But you don't need to do the so the inference is for the labels.
It's for the inferences also the code.
Okay, we did it.
Probably start off wait on.
Yeah, I said it was this one. There was some misspellings. Yeah, so it was calling, so it was a change of 5 minutes. Wasn't it? But I forgot exactly. If I'm looking at it for a week, then I forget all the details.
Hello.
Right.
Yeah, that's how I want to name.
What?
Ragos, well. Well. Thank you. I wasn't sure. Thank you for agreeing to do your presentation.
Yeah, at first I just didn't get what you
Yeah.
but with the same potential. Yeah, of course.
And that the paper is good, so. Do all this stuff.
Sure. Yes, actually, I'm very comfortable with the second presentation. I'm going to do quite a big event just to present a first minute. Otherwise, it's
Yeah, you know, like the presentation slots are getting shorter and shorter.
especially on Slack.
Yeah. And I think like ICFP is as bad as well, because they're trying to have simple facts about everything.
I've heard that it's 25 minutes.
Yes, it's like last year it was 15 minutes.
Someone told me that they got 25 points. I don't know. Someone. But,
Yeah, probably it doesn't count, it's one of the workshops. Okay, I'm gonna go grab some coffee now that they got to them.
yeah, I think I do too. Making sure that my presentation works.
But it seems to work. Try it out, but so far it seems to be quite okay. And we can just share your.
You know, there was a session for Erlang at the very end of the day.
Yes, there will be starting well in the next session slot. So,
Of course. Are you the student volunteer for Erlang?
Yeah.
Can I tell you something to tell the session chair when they get here?
Yeah, of course.
We're asking all of the session chairs of the last session of the day to pull up the directions for how to get to the concert.
Oh,
and tell
sure, yeah.
people to go to the concert.
Cool.
Because otherwise people will just not know.
Yeah, will do.
Thank you.
No worries. have the first speaker, brilliant. And any other speakers in here? The other speakers are cool. I think the other one is remote. So that's the other one. Okay. Should we see if we can get it set up? Just make sure everyone's all right. Are you going to be presenting from your own?
Yeah.
Great.
Okay, so next up we have lightning talk from Radoslav Wiki from the Technical University of Denmark. And he's going to talk to us about DDMon and monitoring tools for distributed deadlock detection.
So, hello everyone. I'm going to present this thing to you to hopefully help you solve all your problems with deadlocks. So problem. Well, deadlocks are the problem. I guess I just have to introduce what a deadlock is. In our work, we focus specifically on generic servers. Who knows what a generic server is in Erlang? Yes, it's like a two-stage pattern in which you essentially spawn a process in which you can make blocking calls. You can send a message and the service picks it up, keeps working on it while it's not doing anything else, so it's doing it completely sequentially, and then it replies to you with a response, and it just handles one such request at a time. Okay. So it's easy to imagine that such systems based on generic servers can run into deadlocks. You can have cycles, and they happen in production. We have evidence from the industry that this is actually a problem. Unfortunately, Erlang provides only with trivial deadlock detection. So if a generic server calls itself, then you get a deadlock notification, of course, because it can detect it. But if a deadlock consists of more processes, which is usually more concerning case, you get no feedback about bad stuff happening other than a timeout simply. So it's hard to distinguish low performance from a deadlock, and also it's hard to get any decent feedback of what processes have been deadlocked. So for this, we introduced DDMon, which is implementation and artifact to our other talk we do at UPSLA, correct black box monitors for distributed deadlock detection. That's the theory. So if you want, we have formalized everything I'm going to say here, and in this talk, I'm going to just describe the implementation. So DDMon is a replacement for generic server, which acts as a wrapper over the actual generic server process. And the aim is to have minimal code intervention, so that if you have a system, you can just easily apply it and have deadlock detection almost for effortlessly. So how you apply it? If your project is written in Erlang, you just replace all references to generic servers with our DDMon module. You can do it manually. You can also use parse transform if you'd like, and then with some basic interfaces should work. In Elixir, you can use alias, which makes things even easier. And if you do it, you just get deadlock notifications whenever they happen. So how does it work? First of all, how DDMon actually interacts with generic servers. So for each generic server in the system, another process is being spawned, a monitor. This is exactly what it looks like, which just oversees communication of one particular generic server. So each generic server receives one monitor. And to make it clear, I don't mean like Erlang monitor, which receives notifications only if the process dies. Like a monitor more comes from the theory of it, and just think about it as a separate process. It's in this model, its job is to intercept all messages and act as a proxy between this generic server and the system. So it receives a message, sees what it is, and then passes it down to the actual server, and the same happens for outgoing messages. In the meantime, this monitor can communicate with special messages called probes with other monitors to establish some knowledge about the global state. So how do we detect deadlocks? Well, the it's not rocket science. We just look for cycles, and so say we have a system based on 3 generic servers. Each one receives a monitor. There comes a call to the first one, which is forward, which is then passed to another one, S2, and reacts to it by calling S3, and S3 calls back S1, and we have a deadlock situation. So in this case, if the monitor observes that it received a request while waiting for a response, it will send this probe message to whoever called it, like against the wait for graph, right? This message gets then propagated, and if it returns before a response is received, that means a deadlock has emerged. As simple as that. And this algorithm we have proven correct. We have done it in Coq, so there's no discussion about it. This whole thing is a model, so if you'd like to see how more details about it, you can just read our UXLA paper or attend the presentation later. I'm going to talk more about testing it. So like just to see how it looks in practice, we created some example system to evaluate the artifact in which we produce microchips. So we have producer processes which produce microchips, whatever data it is, and they call another kind of generic service called inspectors, say, who validate their produce and return OK if it is found. However, inspectors might also call other producers for some reference method data. That's just the story we made up. So if we take as an example a system with 2 producers and 2 inspectors, one can make a call to producer 0, which would then ask inspector 0 to validate its result, and I0 might ask P1 for its metadata reference. And they can receive responses to their calls, and a similar thing can happen in parallel. If, however, in the same scenario, these 2 things would happen in parallel, it's easy to see that they can call themselves, causing this cycle here, and they would not recover. So just to show how it looks in practice, visible. We have this implemented. The code is on GitHub, so if you'd like to see how it works, that's there. You can just find out, put the link later on. Get this clear, so we can run this system, and we see that we non-deterministically get deadlocks. For example, here, the first call to the system yielded a success. This time we got a timeout because a deadlock has emerged, which you can see from the log. However, if we do this completely unsuspicious send command, which uncomments these 2 aliases, that's the only thing it does, we employ our monitoring. So like we replace references to generic server with our system. Then we also need to turn on monitoring. Okay, nothing, no deadlock happened. Yeah, we got an immediate deadlock description. So we can see that the cycle has been detected and the system terminated early without timeout, and we also get the list of processes. So that's how it works. How else we tested it? Well, we performed many auto-generated tests. We created a DSL in Erlang, which allows us to describe specific scenarios of processes communicating with each other and possibly running into clashes. So here we can see this example implemented as in our DSL. So for example, here we have 2 sessions. I0 begins with some initiated process number 0. Then there's a call performed to process number 1, which then calls process number 2. And then they would just receive replies in the opposite order. Meanwhile, I1 does exactly the same thing, just with different processes, except that it waits for random time before that. So using this neat system, we can quite precisely replicate scenarios which appear in real systems and see how the daemon behaves. So we've performed many tests for correctness and also for just to see the performance of the system, like what's the overhead of having it here. So obviously, if you just count blunt messages, the overhead is like 3 times increase in messages sent, because like in order to a single communication turns into 3 messages. That is like forwarding outward, outside, actual communication and forwarding inside. But in practice, we believe that this forwarding is going to be quite a quick operation, because there's no I/O involved if both monitor and the generic server run on the same node. It's just a memory operation. A trick you can do to minimize the number of probes emitted, however, because that's significant if you take a look at this red line, for example, maybe I should say what these numbers mean. The vertical axis says how many messages have been of different types have been exchanged, and horizontal is just time that passed in a quite large randomly generated system. So here, for example, in this chart, we see how many queries and probes and responses have been sent around. The number of probes is quite high. But on this chart on the right side, we implemented some tiny optimization in which we just delay deadlock detection by 5 seconds. So like whenever, instead of initiating this search immediately, we just wait for 5 seconds. If we haven't received a response, we just do this circle detection. And that completely obliterated the use of probes. There's just the overhead of messages just disappeared. So the conclusion is that the overhead is quite small. So just to summarize, DDM provides generic server-based system with deadlock detection. It's quite easy to apply, and its correctness has been proven formally in COC. It's not a production-ready implementation, of course. It's mainly a prototype, but like it proves the point. And that's it. Thank you for attention. Positive views.
Right. So question. So when it detects a deadlock, it will show which were the processes involved, but not the actual calls or.
No, but it's relatively easy. Like since monitors intercept messages, they can see what messages like cause the deadlock as well. So it's just a matter of adding logging. The problem is like if you send a lot of data, then you have to store it somehow, for example, and that might be inefficient depending on how you would like to save this information.
Maybe have some kind of tag of the messages you want to say.
Yeah, this is a possible extension, but sure. Yeah. Also, maybe what I should have said, which I didn't, is that it neatly allows to distinguish the processes which participate in the cycle from processes which are dependent on the cycle because they call some deadlock process. Because technically those also are going to await infinity, but they are not the source of the issue. The source of very information in debugging.
One more question. So you said that the optimization is delayed when you start doing the cycle check, just to see that something seems stuck, if I understood correctly.
Yeah, so like if we go back to this animation, so when a call happens to it, when a call is received by a monitor whose generic server is locked, but because it's waiting for a reply, it can just, instead of sending this probe immediately, it can just wait for some time. That's easy to configure and it has huge impact on.
And the time is proportional or is dependent on the timeout of the call, or it's
it should be like adjusted to the size of this cycle and like the sum of all those calls. Because the cycle is big, then I guess you can receive a reply after a long time.
Can everything time out before you start?
Okay, so in this situation, we assume no timeouts. Okay. So because if you have a timeout, then you technically, like theoretically, don't get deadlocked because you don't actually need to receive a reply in order to proceed. That's the philosophy here, because if you apply timeouts, then actually there's another way, and deadlocks are supposed to be permanent.
Still an error to usually have a timeout and abort, like sometimes you have the timeout on the call and just fail, and in the log you will have got something timed out and you still don't know why it happens.
Well, if you have timeouts, then yeah, you will not get with deadlock detection. That's like if with this you should not use timeouts to handle deadlocks. Essentially.
Can I start to qualify? So, as Tadek said, you should configure delay so that the probe is sent maybe before your timeouts expire. Otherwise, you may get basically incorrect deadlock notifications. And at the moment, basically, we've proven that every deadlock report is precise. So if there's a deadlock, it's reported. If a deadlock is reported, it is real. But if you put timeouts in the mix, then you may get notified about a deadlock that was resolved by a timeout before. Maybe it's still good, depending on your application, but it is setting you decide not to do that.
One thing is that, okay, but also, I think the bigger problem is actually that monitors don't really know what the timeout is of. Like this information is not propagated forward; it stays in the generic server, so the monitor kind of know when to abandon the call. Yeah.
Yes, just to understand your point. So as far as I understand, having a cycle among actors is not the only condition for the deadline. So to have a deadline, if I remember what I learned from operating system courses, there were 4 conditions for the deadline, and one of them is having a cycle. So probably your algorithm, so you do not explain all the detail of the algorithm. Perhaps there are more than checking the cycle. That is my understanding.
So with this, like, assuming we are talking about generic servers which do not do timeouts, we model that in hoc, and we have a proof that being deadlocked is equivalent to having a dependency cycle in the network.
Having a cycle.
Yeah, because the definition you're referring to likely is first of all more global, so it requires that the whole system is actually stuck. Here we are talking just about local deadlocks, where just a part of the system can get blocked. And as far as I remember, the definition I've been taught, they were usually referring to common resources, and here we are talking about message passing. Like you can model them as resources, but it's slightly different setup. Yeah, be good. And thank you for your attention.
So next up, we have remote lightning talk. Going to be given by Melinda talk about securing Erlang and Elixir application.
Yes.
Hello, can you hear me?
Yeah, we can hear you.
Great. Let me share my screen, at least my presentation. Okay. Can you see my presentation?
Yeah, we can see the PowerPoint app. Oh yeah, there we go. Yeah, perfect.
Okay, great. Hello, everyone. I'm Melinda. I'm an associate professor at the Eötvös Loránd University. I know that I'm not the only one from the university today, so please listen to my talk, one more research topic of LTAP. Today, I would like to quickly introduce you to our security analysis tools that can identify different vulnerabilities in Erlang and also in Elixir applications. Our work started quite a long time ago. Already in 2020, we had a talk at the Erlang workshop. Actually, one of my students presented our approach, that how we try to support secure coding with Refactorer. Actually, at the same time or at the same year, the Erlang Ecosystem Foundation established the security working group for providing and creating secure coding recommendations for Erlang and later Elixir applications. Actually, that time, just 5 years ago, we've used a bit different terminology, but actually we listed almost the same potential risk related to Erlang security or related to Erlang applications. Our approach, our static analysis approach to identify security issues in Erlang application is based on the Refactorer tool. Refactorer is a static source code analysis and transformation tool designed originally for Erlang. It has several features to support software maintenance and development. We have, for example, lots of features related to code comprehension. We provide a nice query language to ask information about the source code. We have built-in queries, and the developer can build their own queries about the source code, asking information or dependencies among source code components. From the name, you can deduce that the tool was originally designed for refactorings. So we have lots of transformations that we offer for the developers. And in the last years, we are focusing on source code checking different properties of the code. That may include some very simple properties about the structure of the code or the dependencies, like some linting features. But nowadays we are focusing, or not just nowadays, but since a few years, we are focusing on checking security properties of the software. So how this working? So we have the Erlang source code, and what we do is that we build an internal representation from the source code. Actually, that representation is a 3-layered semantic program graph. Because of the original design of refactoring, we store the original layout and the lexical layer of the code. And we build a syntax tree. This is our custom syntax tree. And then we perform lots of static analysis, static semantic analysis on the syntax tree, and store the result in our internal representation. When I'm talking about semantic analysis, you can think about very simple ones like calculating the binding structure of the variables, or storing and calculating a static call graph. But for example, we also calculate side effects of functions or the dynamic calls, dynamic call information available or calculable from the source code. We have data flow analysis to calculate the values of certain expressions. We can also perform control flow analysis using this representation. So this is a very extensive framework, semantic analyzer framework. And we use this internal representation for the security analysis as well. We look for, in the analysis part, we look for certain patterns that may represent a potential vulnerability, a potential risk in the source code. What we do is that we look into the syntactic and semantic information available in the graph and create a set of initial candidates that might hold vulnerability. But obviously that candidate list contains lots of false positive hits. So we apply, based on the semantic information available, we apply an false positive filtering on the candidate list. And we try, it's an extensible framework. So we try to drop most of the false positive hits from the candidate list, but you have to know that this is a static analysis. So we are conservative in the sense that if we cannot decide from a candidate that whether it's vulnerable or not, then we keep it in the candidate list. And at the end, we generate a report or a list of potential vulnerabilities based on the syntactic and lexical layer of the semantic program graph. What we have in the open source version of Refactorer that we created proof of concept implementations, we have around 20 so-called checkers, security checkers that's able to identify vulnerabilities in the source code. The results can be visualized in different ways. You can use the web interface of Refactorer and click on the vulnerability, and then it will be highlighted in the source code, or you can use simple command line interfaces and then just have the context and the expression that's potentially vulnerable. We applied our tool on several open source projects and found lots of potential vulnerabilities. We can conclude that the majority of the issues, 2/3 of the issues related to denial of service attacks through atom exhaustion. So that's the most common vulnerability in the Erlang ecosystem. We found injection-related issues as well, like OS injection, OS command injection, or beam file, unverified beam file loading, or similar issues as well. We just to provide you an example, in the OpenID Connect Client library, we applied the security on the source of the library. We applied our security analysis. We found that an issue that we reported, and it's already fixed. So OpenID is safe to use. And so that was our original work related to Erlang, and then we presented this almost 2 years ago at the Code Beam, and then lots of Elixir developers asked that, okay, you can do it for Erlang, but whether you can do it for Elixir as well. And from the static analysis point of view, if you wanted to build, we believe that usually static analysis is something that is a language semantic dependent work. So whenever you wanted to do something for a programming language, then you have to analyze the source code and build an appropriate representation and build an analyzer framework that is designed and built according to the semantics of the language. But we did not want it to do it for Elixir, since we had an Erlang analyzer framework, and and everybody knows that actually there are two different syntax, but the semantics is quite similar or the same, because the Erlang virtual machine will evaluate and run the code either if it's written in Erlang or Elixir. So what we were thinking about, that whether we can use our representation to represent somehow the Elixir source code and then apply our analysis on the same representation. And we are lucky because whenever you compile an Elixir application, then the Elixir compiler creates the Erlang-ish version of the Elixir code, which is the abstract code in the Erlang abstract format, which is actually a syntax tree. And we also have a syntax tree in the semantic program graph. And what we did is that we take the Elixir, compiled Elixir application, ask for the, read the abstract code from the compiled Beam files, and actually take that syntax tree and map that syntax tree to the refactorer syntax tree. So basically, we drop the lexical and syntactic analysis of refactorer. We build directly the syntax tree from the abstract code, and then we can apply the same semantic analysis that we designed. Since it's an Erlang syntax tree, the semantic is the same as when we build it from the source code in case of Erlang applications. So we can apply the same semantic analysis on it that are already implemented in refactorer. And then we tried whether it results vulnerabilities or whether the security analysis is working for Elixir applications on that representation. And yeah, that works perfectly. And doing anything, we were able to spot lots of vulnerabilities in Elixir applications as well. So we just changed the very first step, which is the intermediate source code representation generation. So we load the graph or create the graph from the Beam code. But obviously, there are some differences in the Erlang and Elixir analysis. Obviously, we had to add new checkers because we can spot. So once we have an Elixir construct and then it compiled to some Erlang library functions. For example, there are lots of string interpolations that compiles to binary to atom function call inside during the compilation, so we can immediately spot it. So we have the Erlangish representation that's a binary to atom, so that's potentially vulnerable. So we just apply the same security analysis on it, and we can spot it. But Elixir has its own standard library that has its own vulnerabilities. So we had to add new checkers reflecting to the Elixir standard library. There is a significant difference in the result of the Elixir and Erlang application candidate list is that in case of Erlang, we can exactly mark the expression that is vulnerable in the source code because we have the original syntax and the original code with the position information and everything. But in case of Elixir, during the compilation, we actually lose the original syntax and also the position expression range information. We have just a line information in the abstract code. We try to keep that one and annotate our syntax tree with the generated line information. And in the results, in the candidate list, we use that line and we try to, when we generate a vulnerability list, we can point the Elixir module and the line in the line information is presented that this line contains. We don't know that exactly which construct in that line, but we can point the line in the result. And also we started and we are working on domain-specific analysis related to Elixir. We try to process and support the EF's application security, web application security best practices, and whenever it's possible to list the vulnerabilities that we can identify in the source code, like the common stuff through Acto, SQL injection, or some cross-site scripting attacks, and so on. So we've also added checkers for that. So if you ask me that what should I do if I want to secure my Erlang or Elixir application, then I can say that there is a single tool that can do it for you, and that's safe. You can ask that I was talking so far about refactorer and why I'm talking about safe now, because we have a collaboration with Erlang Solutions, and we created the safe tool, which is stands for security audit for Erlang and Elixir. The safe is using the vulnerability detector implemented based on the refactorer semantic analysis framework. It can be used either as a one-time audit. So if you just wanted to list your vulnerabilities, you can ask Erlang Solutions for a one-time audit for your source code. Or even if you want, you can integrate safe into your CI pipeline and continuously check the security or the issues in your application. And just a final note from my side is that you've heard lots of talks from my university today, and one of them was by Gergo that was talking about formally proving the existence of atom exhaustion through the list to atom calls. And you may ask that, okay, I'm talking about tools now. One of my colleagues talked about formally proving security properties. Is there any connection between the two approaches? Yes, there is a connection that both of the approaches are provided and implemented within the Ötös-Loránd University, but SAFE does not include any formally verified property at the moment. But we will see what comes. Gergő's supervisor, Daniel Horpács, is just next to my office. So we will work on the formally proven properties as well. But you have to know that this is not an easy task. So we will see when we can reach a point when an industrial proven tool like SAFE can use formally verified approaches for security identification. Thank you for your attention.
Any questions? Well, thank Melinda again.
Thank you.
Thank you, Melinda. And thank you everyone for coming to the 24th edition of the Erlang workshop. Big thank you to all of the authors, all of the presenters, and everyone that's attended. Big thank you to the ICFP SPLASH organizers as well. And to our sponsors, Erlang Ecosystem Foundation, Ericsson, Dashbit, and Erlang Solutions. So let's give them a round of applause. And lastly, Farm would like to invite everyone to their evening of performance. So I think that their website has all of the details, and I'm pretty sure we'll find them outside in the hallway. Thank you.